Good morning, ladies and gentlemen. Good morning, dear team, dear partners, colleagues, and to the entire audience. We are very pleased today to welcome you to this webinar of this CLUG project, for which the entire team has been working very hard during the last 30 months. And we are very happy to present to you today the results that has been achieved in this very interesting and amazing project. Let me introduce you first to my co-moderator today, which is Yasmin Jesonovsky. We will moderate the sessions today, introduce our guests, and will also be your timekeeper and available for questions. There will be a lot to discuss today. So this is why we have scheduled multiple Q&A sessions throughout the entire agenda today. You are able to ask questions after or during every presentation, which will be received by the team for moderation. Once a question has been released in the Q&A section, you are able to vote on the popular questions or questions that are most interesting or important to you. Please use the according teams function, which is provided in the tool. Questions will then be answered in each Q&A section according to the popularity. Please understand that we may not be able to answer every question received due to time constraints. This is also a live webinar, so you are able, nevertheless, to exit or re-enter the webinar using your link at any point in time. You may also pause or skip the webinar at any point if you want. But please understand that if you do this, you may not be seeing the live progress. We advise you to use the live function at any point in time so that the progress and the content presented is matching the agenda. And please also try to ask questions that are relevant to the current speakers or the last sessions that have been presenting. Otherwise, we will try to moderate the questions, answer technical issues directly, and provide only relevant questions to the current section. Now, let's dive right into the webinar. Let me introduce our first guest of today, which is Annika Hundertmark from Deutsche Bahn. Annika is the head of the railway digitalization at Deutsche Bahn. Annika, I leave the floor to you to introduce our today's session and for a very warm welcome address to our audience. You are now live.
Thank you, Florian. Yeah, hello also from my side. I really welcome you to this webinar here, and I'm really looking forward, and you can really also look forward to all the interesting things you are going to see today. So yeah, let me start with a short introduction. I'm standing here as a European citizen, as we all, I hope. And as a European citizen, I have a wish. And the wish is also quite simple and also, I think, quite known, which is that we need to make the world a bit more sustainable. And we all have the possibility to do so. On European level, we have made a very big step with the Green Deal. So we have a very good foundation, having all the countries at the same table, aiming at carbon neutrality, let me add, at latest by 2050. This is very important. And what we know also is that luckily and unfortunately, the transport sector has really a big part on that. So the transport sector is really mission critical when it comes to achieving this target. So what about transport sector? So the transport sector is big, yes. And however, the modal split of railways is low. It's, from my perspective, ridiculously low. Yeah, we're talking about like lower than 10% for passengers, a bit more than 10% for goods. And we need to change this. So this is the positive part of the story. There is much room for improvement, and we really have a chance to make a difference here. So what is needed for making this difference and for increasing the modal split, because we all want to make railways more successful? In the end, we need to get more customers into our system. And what is needed for getting more customers? Good offers, of course. Yeah? Good offers, good price. But from an operational perspective, what do we need? We need more capacity, and now especially focusing on the German perspective, we really need to increase the quality. And in the end, we need to have a really reliable system. In Germany, Florian introduced me also as being part of the program Digitalisation in Deutschland, Digital Rail for Germany. We are tackling these challenges or trying to increase capacity, quality, and so on with this program. You must know that in Germany, the infrastructure is quite old. And therefore, for us, it's a very important step that we start with a renewal of the infrastructure, so meaning ETCS and digital interlockings. So we have already started, and that we have this as a first stage and start with the rollout of that. But at the same time, we are working on a second stage of this program, which has a quite ambitious target picture, which most of you know, and also, at least as I know, share also. The target picture is as follows. We have trains which run automated in optimal distance and which are steered optimally throughout the network in real time. So that easy, that short, that easy, that complicated. And it's really important now that we can make use of GNSS in that, because you know that GNSS is crucial when it comes, for example, to moving block. Yeah? We need a train-centric, reliable, and very precise localization in order to make moving block happen. But also we needed the precise localization as an enabler for ATO and also for the capacity and traffic management system. And in the end, I was talking about the products, and also customers want products for a good price. Of course, we hope that we can realize that we can reduce the number of infrastructure elements in our system, making the system cheaper when it comes to maintenance, for example, in addition to the investments at the beginning, and also more reliable, because things which are not there cannot be broken. And yeah, this was like the plaidoyer, why we need GNSS, why it's so important. I think all of you know, because otherwise you wouldn't be here. What is important now is I realized, or I remember, like, I think it was beginning 2019, and we were at a meeting room here in Berlin, and I had just a table. There was just a table with different partners, so other infrastructure operators, industry, and so on. And there were many working packages. And then there were working packages, number of hours, I think, capacity. So it was just an Excel sheet. I think we already printed it out. It was before Corona. And we talked about this, and we talked about, okay, who could do what, who could take over which working package. And I'm really happy that now all these entities, so which you can read here, I hope you can see this, together has achieved what was back then only paper, that we have achieved a better understanding of how we can make use of GNSS in railways. That we were able to formulate these requirements, and not only as operators, but also together with the industry. And yeah, I think we can really be really proud on what has happened in the last years and last periods. Of course, I would like to get also transfer a special thank to OISPAR, because with you, without you, it wouldn't have been possible. And I'm really looking forward to what's coming after this CLUG 1. Of course, we know that we need to convince our stakeholders, but what is very clear is that we have enough things to do. There are. This is just the beginning. We know not now how to use it, but we need a product then back then in some years in order to achieve these ambitious target picture. And I'm really looking forward on getting more and more forward on that way together on a European level with all these European partners. And for today, I really wish you lots of fun. We have had this physical presentation already in France, so I know what's coming, so I can promise you it's really interesting. Thank you to everybody who contributed to the project. And thank you also to everybody who prepared today's webinar, because I think it's really important that we share the interesting and good news of what we have achieved with CLUG here in an audience. Yeah, having said this, just have fun. Thank you for your interest and your attention. And I'm handing back to Florian, I think.
Thank you very much, Annika, and thank you for this warm welcome and the good introduction. I am very much looking forward also to this day now, to the webinar and all the interesting presentations and insight that will be presented during the day. The next upcoming presentation introduction will introduce USPA. USPA is the European Union Agency for Space Applications, and USPA is also the funding entity of the CLUG project in these activities. Therefore, I really would like to express a big thank you again and a dedicated warm welcome to USPA. USPA is supporting the European space contribution to the railway sector and railway signaling, and conducts a lot of supportive actions aiming to allow the European railways and the space stakeholders to introduce Galileo and Egnos to ETCS, the European Rail Traffic Management System. I am very honored to welcome now Daniel Lepur from USPA. Daniel is the CLUG project officer from USPA, who will present us the USPA strategy for the rail sector. Daniel, the stage is yours. Welcome.
Thank you very much, Florian, and thank you very much, Annika, also for your introduction. I will try to share my screen for a couple of slides that I prepared for you. I hope that you can see it well. So in fact, in the upcoming 10 minutes, I would like to share with you a couple more information about what we are doing in the rail segment and what are our ambitions in the wider term, also for what concerns EU space solutions, targeting, of course, railway as one of the market segments for their future adoption. For what concerns our agency, I think that maybe all of you know us more under the acronym GSA from the past, but we transformed to EUSPA in the last year to reflect somehow the changes that are actually happening also throughout our entire space set of activities from the European Union point of view, and outside of taking care of Galileo and Egnos, as you were used to with us in the past, we also received on board and we are taking care of additional activities, such as, for example, the market development activities for Copernicus program, but also for the GovSatcom, which is an acronym for the governmental, if you wish, satellite communication services, which also could potentially offer additional connectivity elements for many different applications. There is even a debate to still support its wider expansion towards the transport segment. So we do also expect that secure satellite communication will find its way to support even our application that we'll be discussing today about, which is the railway signaling in the longer term. However, we still continue to follow our original mission, which is to support exploitation and security of Galileo and Egnos, and run all the management operations, infrastructure, and also evolutions, last but not least, of both GNSS systems. For what concerns adoption itself, we started before 2010 with market development and adoption activities in many market segments. As you can see on the slide, there is a lot of success stories that we can share. There are billions of devices that are Galileo enabled already today. Of course, the most massively visible segment is the smartphones or the consumer segment with most of the devices relatively simple. But there are much more sophisticated segments, like, for example, starting from road, there is a significant adoption for what concerns, for example, safety applications in the road, like the eCall, or for what concerns aviation safety related applications, like support of the aircraft within the approach procedures for landings at European airports. And here we are getting also maybe to a connection with rail somehow, because the point for aviation and for rail is to a certain extent similar, I would say. It's not only about improving the consumer experience, but also to help ourselves as European society to save the costs that are related with the operation of the infrastructure. And in aviation, for the approaches, actually quite an expensive infrastructure is used. For example, it is necessary also for the aircraft to follow a predefined straight trajectory during the final landing phase, so it's not possible to land in a curve, if you wish to explain it simply. So also the economical impact is becoming very important at this stage. And in railways, we are trying, at least for what concerns our approach in signaling, to go in the same direction, to actually help the society and help railways to drive the cost outside of the infrastructure management, if possible. And this is mainly what our projects, and it's not only CLUG, but also the past projects that were carried out. Let me mention, for example, state-of-art projects from the past, like STARS, that some of you could know, or ERSAT, that they are aiming for. But despite we are having quite a success for what concerns non-safety critical applications in rail, like, for example, you see on the left side of the slide the asset tracking, wagon telematic solutions, which were, by the way, also piloted and kicked off by Deutsche Bahn in 2016-17 with the wagon tracking solutions. With signaling, we are not yet there. There are really many applications where GNSS is used already in rail, but for ERTMS and for the safety critical part, we still have activities to do before we can finalize and implement. However, still, I would like to mention, when we are talking about it from the perspective of development, if I can share my opinion with you, at this stage, after CLUG, we are actually in a different situation than 2 years ago. Now, what we have and what we visibly see also coming from the stakeholder initiatives and from Deutsche Bahn, SNCF, SBB, and the CLUG consortium, is a sort of a higher level commitment, which is promising to drive this solution forward in a coordinated way, to make sure that it can be in the future adopted, and that the TSI, the technical specifications for interoperability of ETCS, can be hopefully modified in the future, favoring GNSS as the localization technology of the future, wherever useful and wherever it contributes to decrease the cost of the railway signaling. For what concerns Galileo as an enabler for digitalization, I would like to share with you also this small success story that should be emphasized always as a starting point for Galileo in rail, which is the simple application of asset tracking. It indeed contributes to actually creating a level playing field between rail and road, also providing accurate information about the train location, and especially about the cargo location for the rail freight. And it binds also to several business processes that are important for the railway. So this information is not only used by the operators to know exactly and in real time where the train actually is, but also for the customers in order to provide them with more accurate services, starting of course from a better estimation of the time of arrival, but it's going down, for example, to a timely invoicing of the goods service that has been provided, the transport services. So we have more than 100,000 wagons already equipped around Europe with GNSS-enabled telematic devices, which is quite a success. What we are doing in signaling as a USPA to support further the adoption, we are acting basically on the basis of the European Parliament actually a resolution of the 7th of July. To be more concrete with you, it's available, of course, in the archive, where you can check yourself that the European Parliament made several quite important conclusions on the necessity to support GNSS and the ETCS coordination in the future and the uptake as soon as possible, and is inviting all the stakeholders and especially the railway signaling industry to contribute towards closing of the gaps that are still technologically present in order to be able to start to use the solution on a wider scale and include this element into the upcoming TSIs. So we are closely coordinating, of course, with the European Railway Agency on this and the ERJU, the joint undertaking. This has been also the case of the past with Shift2Rail. So you might have noticed also that there were several projects from the Shift2Rail, very successful, that contributed also as a part, specific work packages to the GNSS evolution and possibilities for its adoption. We will continue with this, and we will participate also as an observer to the system pillar steering group in order to make sure that the activities between rail and space are coordinated and that we can contribute also from our technical capacity together with the European Space Agency or ESSP, or which is the European Satellite Service Provider, the service provider of Egnos, and the GSC, the Galileo, basically service center, which has got engineers to be able to support eventually wherever needed for what concerns Galileo and Egnos. For what concerns ERTMS change request 1368, just one small comment. We are actually working together with the ERTMS users group in order to finalize and update this change request also as an input towards further Europe's Rail joint undertaking initiatives to be able to build on something concrete. This change request, as you might also be aware, is dealing with the problematic of standardizing augmentation solution and including augmentation, namely Egnos, plus other possibilities into the TSI in the future, and is also opening the topic of the digital maps, which is a very significant underlying element for localization that still needs to be tackled within the preparatory activities. We are at EUSPA working also on the defining of eGNSS service for rail. So at the moment, there are two mission studies that are in the conclusion phase. They will be closed very soon, and their objective is to consolidate an implementation roadmap for a dedicated Egnos service for rail, to define the milestones that need to be carried out in order to make the service available for the railways as soon as possible. Optimally for a test phase in 2025, and then later on as indicated within the timeline associated with Egnos V3, the third generation of the system. And we have also fundamental elements program that we are running, which is another R&D element focusing on the receiver and antenna development, or the underlying elements in more concrete terms. Here we have two projects focusing on rail that should develop a sandbox for rail safety relevant receiver and antenna in 2023. Yes, indeed, we are also providing a roadmap, consolidating it together with our stakeholders from signaling environment, with the associations and with European Railway Agency and the Space Agency. And we continue to support also additional research and development programs. So Horizon Europe, in Horizon Europe, there was a call has been closed just now and is under evaluation, but there will be also other calls to which I have still a slide for you. But to summarize the projects in rail that are currently running, we have of course CLUG, about which you will learn from my colleagues, so I will not comment over there because this is the objective of the webinar today. Additional projects that are still ongoing, helmet, rail gap and radius. For helmet, it's trying to develop a high integrity and accuracy platform for signaling, benefiting from the perspective that many of the railway lines and the road network are adjacent with each other. So they are trying to optimize the cost by developing a joint augmentation network for the difficult environments of both segments, if you wish. Then Rail Gap is tackling the topic of the digital map, designing some specific tools for supporting, again, integrity and accuracy in ground truth for development of accurate trackside maps. Last but not least, also Radius is looking more into the combining drones with rail in the most efficient way in order to be able to contribute to safety and non-safety critical applications, both of them, especially with within the asset management part of railway activities. For what concerns the upcoming R&D initiatives, so within EUSPA, we will have another call opened at the end of this year. It's already present in the work program. You can check it for more details in the work program, but just in general terms, there is going to be a specific chapter for smart mobility applications where also rail projects could be submitted, because the objective of this special chapter of the call is focus on, let's say, segments that are developing with a longer lead time and with safety constraints. So from our perspective, it is a fit for sure for all our transport segments, but rail specifically, because railways are actually nowadays, as Annika already indicated, considered, and they are indeed a very significant contributor to the greenification of Europe, and the Green Deal itself is emphasizing that as transport in general is contributing heavily to CO2 and other different problematic elements production. It is necessary to facilitate further the shift, especially from road to rail in terms of cargo. And over there, I think that GNSS can play an important role further on to decrease the cost and make railways actually digitalized and more efficient from signaling point of view, hopefully as well. We have in this innovation action approximately 9.5 million euros available for the project. So I would like to invite you to also try to again showcase that rail is interested in space and willing to drive the initiative, especially in signaling further on, to conclude and to be able to celebrate very soon, hopefully within the next upcoming TSIs, already a point where we could say that we managed finally to ensure that GNSS can be adopted and used for railway safety and signaling application, namely in ERTMS. Thank you very much. This is all from my side, ladies and gentlemen, and I hand over back to Florian for the next. Thank you.
Yeah, thank you very much, Daniel, for this interesting insight and the general overview. And without any further delay, let's have a next overview of the CLUG project itself, its mission and objectives, as well as organization and the structure of the project. We will also have a quick look at the main topics that have been researched and delivered in the project and work packages, which we are going to share later today. To provide you this general overall project presentations, I am now very pleased to welcome Valentin Barrault from SNCF. Valentin is the CLUG project coordinator and also a localization project manager at SNCF. Welcome, Valentin. The stage is yours.
Well, thank you for this introduction, Florian. So nothing else to add on this presentation slide here. I will go on the next one. So regarding, so I will introduce indeed the project and the context of the project first. So the context of the project, there is a clear push of Europe toward the introduction of GNSS in railway. So we had the ERA report from 2015 first, stating that the strain-borne localization function based on satellite positioning is a game changer for railway. And also the European Parliament report of last July that Daniel mentioned right before, also calling for a joint effort toward the introduction of GNSS in the ERTMS deployment. So yeah, clear push of Europe, and on top of that, also the Green Deal that Daniel mentioned, for which, well, so for which there is some clear move of railway toward digitalization and sustainability to fulfill the ambition of the European Green Deal. So our ambitions have been driven by all of this, on top of the fact that we would like to also to decrease the cost of the RTMS signaling system in the future, as it is relatively expensive in the current version. So our goal is really to move away ERTMS from trackside-based detection system to onboard safe navigation system using multi-sensor fusion and with the aid of the European Global Satellite Navigation System, so EGNSS. EGNSS regroups Galileo, the European constellation, but also Egnos, the European augmentation service that provides corrections to a GNSS receiver to improve the accuracy and the safety of the position computed by the receiver. But we'll come back on that later in a presentation made by one of my colleagues. So the main challenge for our project and for rail in general is, and for using this kind of solution, multi-sensor fusion solution in railway, is really to deliver a solution with the required performance and safety levels in railway. Required safety level, so meaning CIL4 level, which is a really high safety level when we compare it to what is required in aviation or automotive. And therefore, having this kind of technology, which is well known and used in some other domain, is challenging for railway with respect to this safety level. On top of the fact that we have very constraining and complicated environments that doesn't help to use this kind of signal GNSS technologies. So we want to have a safe onboard localization unit, but what for? The idea is really to have a solution that is oriented toward the need of the future railway system. This is not exactly the case of the current ERTMS system based on the odometry function and on balises or on the ground. it's quite static and not very flexible. So we want something much more flexible. For what needs, so the idea is really to optimize the line capacity by reducing headway between trains, and this kind of solution could be a facilitator of ERTMS level 3 moving block. We also need a cheaper signaling system with less Eurobalises and also other track equipment that could be reduced along the tracks, with the final goal to improve the economical balance of the ERTMS signaling system. We also need an advanced traffic management and control system, and eventually we would also need better customer satisfaction. It was also mentioned before by Daniel and Annika, but the idea is really to increase the modal part of rail. And if we want to increase the modal part of rail, we of course need the customer to be satisfied, and enabling some comfort function such as the real-time train tracking could help in this goal. So for what kind of applications would use or would be defined to fulfill all of this need? We have two types of applications: safe applications on one side and non-safe application on the other side. Regarding the safe applications, so we have the train protection system that is using safe position data to navigate the train on the rail, or the incident management system that is also that would also use this kind of safe data. On the non-safe side, so I was mentioning right before the passenger information system with a comfort function. This would be one, or the perception module would be another one. This module is used by the autonomous train, notably to detect the environment around the train, and so it would need an accurate position of the train and orientation of the train for that. So as you can see, many applications would use the position information released by this kind of solution. I also mentioned the fact that we would need an economical balance, and indeed this balance has to be found between the cost of the infrastructure manager on one side and the cost of the railway undertaking on the other side. So reducing the trackside equipment will decrease the CapEx and OpEx cost for the infrastructure manager. However, changing the onboard system may increase the cost of the railway undertaking, as the current system is not that expensive on board the train, the odometry sensors and all. We have to take care of that. So if we want to achieve this transformation toward this new kind of technology and solutions, the onboard localization system must remain affordable so that both IM and RU can be winning in the change, in the shift. So we are making currently economical analysis so that we can check the final economical balance between both. So let's come back to the CLUG project now that I introduced a bit the context and the overall goals. The CLUG project aimed to perform a mission analysis and a preliminary feasibility study of a fail-safe onboard localization unit. So the idea is really not to fully develop a solution, but to prove that it can work with this kind of technology. So we had 4 main objectives. The first one was to define some mission requirements. Second one related to the definition of an architecture for our solution, and also the development of proof of concept algorithms. Third one is related to the certification of this kind of solution. So, well, we are not going to develop fully a solution, so we are not going to certify it as well, of course. But the idea is to define the steps towards certification that would be necessary for such a localization system. And the last objective is really related to the demonstration of the feasibility of this multi-sensor approach, so with data collection and analysis to be performed. So you can see on this picture the CLUG concept, so placing the system, the TLOBU, train localization on board unit, on board the train, of course, with all the sensors and in interaction with the external elements. So external elements, so user applications using the output of the TLOBU, of course, but also the satellites that are providing their signal to the GNSS antenna. Also the Egnos satellites that are currently in the space. But also there is a radio connection with the trackside, so that the trackside can provide the digital map potentially, and potentially also some Egnos corrections coming from the ground. So it could come from the space, but from the ground also. We'll come back on that later in also the presentation related to Egnos for more detail. But this gives you at least an overview of how where is our system on the train and with what it interacts around it. So regarding the CLUG project identity, so well, it was already mentioned that the project is funded by the European Commission and coordinated by USPA. The project lasted for 30 months. We are now in the final stage of the project. The project ended at the end of May, so it's really now the end, hence this presentation. The project cost is 3.8 million euros with 70% subvention from the European Commission, leaving 30% of investment for the companies. And on the bottom of the slide, you can see the CLUG website on which you can find information on the project. You can also find the public deliverables that have been published, and also some news and information about what we have been doing in the project. There is also the LinkedIn link to of our project, from which we also push news about the project, about what we have been doing. The CLUG consortium, so it's composed of 10 companies coming from 4 different European countries with a very broad mix of expertise. We had rail operators working with rail industrials, of course, but also stakeholders from aerospace and also automotive. And also we had certification experts to make these certification steps that we were talking before. So very broad mix of expertise that allowed us to bring CLUG to very positive conclusions. And eventually on this slide, you can see the work project, the project organization with 5 different work packages, so very classical, nothing fancy here. Work package 1 for the project management, work package 2 where we had defined the mission and system requirement. Work package 3 where we designed the system and developed the proof of concept. Work package 4 for the testing and evaluation with the data analysis. And the work package 5 mostly related to dissemination, where we gathered most of the outputs coming from the other work package to put them in public deliverables, and also where we defined the certification steps for the future. So that's all for my part. I will now give back the hand to Florian, and there is now, I think, a Q&A session actually.
Correct. Thank you, Valentin, and thank you for this overview. Later today, we will share a lot more insights into all those project results, deliverables, and those work packages you have just presented. So during this morning, first step will be the presentation of what has been done regarding the requirements and also the system design with all the experts and actors that have been worked on this part and project. And the first part of the afternoon afterwards will be related to assessing the results of the CLUG project itself, the data collection and evaluation, and also the future work towards the European Railways ambition in this sector. Thank you to all the speakers already, to DB, USPA and SNCF for welcoming and starting this webinar today. And now I hand over to Yasmin for the first Q&A section of the day already announced. Hello, Yasmin.
Hi, Florian. So, hello, everybody. My name is Yasmin, also from Digitalisation Deutschland, and I'm supporting Florian today with the Q&A session. So now it's time actually for our first Q&A session. We will have two more before the lunch break. And as you probably already saw, we have posted the questions in the chat. So let's have a look at the questions. So first question is for Daniel. When is the deadline for the GNSS application for smart mobility call? Daniel, could you answer that?
Yes, for sure. Maybe it's also my mistake that I did not explain properly during the presentation, so sorry for that. It is actually not published yet. It's in the work program, and there is a time slot somehow more or less associated to that with a more detailed explanation that I was able to put in the slide. So in the slide, it was just about somehow clarifying with the audience which might be interested. However, it is foreseen to be opened during this autumn. So you can expect approximately the same timings like with the last call that has been just closed in spring this year. I hope that this helps. Thank you.
Thanks, Daniel. So we have another question for Annika, I think. So does the €9 ticket for public transportation have any impact on the digitalization strategy? And is there the mobility data being used for traffic management?
Okay, interesting question. So first of all, let me shortly explain the €9 ticket, because I'm sure that not everyone listening currently is from Germany. So the €9 ticket is part of a relief package of politics due to the increasing costs for energy and so on, not only, but of course also due to the terrible things happening in the Ukraine. And the €9 ticket is valid for, also you have to pay €9 for 1 month, and it's offered for 3 months. So you can buy the €9 tickets for June, July, and August. And what is now interesting is that the final decision was made end of May. Yeah, and it started 1st of June. So to be honest, it's a big experiment. And of course, like from a railway perspective, this came in just a logical second, huh? Because what everybody then had to do was to like gather all the trains and people available together in order to increase the offer and so on. Yeah. And I'm a big fan of these €9 tickets. Yeah, there are also people who are not in favor, saying, yes, this is too much for the German railway system, and the quality is so bad, and if we have crowded trains, this does not bring more people into the trains, but more tries to like kick people out of the system, because once they've tried, they make bad experience and so on. Yeah, I don't share this. I also, of course, see these problems and these potential problems, but what is the like the first results we already see. So it's just overwhelming, the success. Yeah? So there were so many tickets sold, and this is the first really important thing for us, because it shows that people are interested in public transport. It's valid. Sorry, it's valid in public transport and regional trains. So not in long distance, but it's in regional trains throughout Germany. Yeah, you can go wherever you want. And the overwhelming success of this, so only DB, I think, sold something like 7 million €9 tickets. So in addition to all these people who already have subscriptions, showed the huge interest. So, and this is, of course, a very important sign also to politics, because politics is the one who is in charge, of course, of providing, for example, also support for new infrastructure and so on. And they now see in reality that there's demand for transport services here, and therefore that there is more capacity needed on the tracks. And now this fits to our strategy, so it does not really change the strategy, because we only gain this capacity and also the additional functionality aspects and so on I already mentioned, if we make use of digitalization, because only with digitalization we can increase at like more or less short notice the capacity, because it's not possible to build like millions of kilometers of thousands of kilometers of new tracks. So it doesn't change it, but it really underlines what underlines our plans, of course. Second thing, of course, this kind of experiment is accompanied by many analyses and studies and so on. So it's better, of course, to understand people who before were not customers. Yeah, so we gain much information, and of course I'm quite sure, so to be honest I don't know, but I'm quite sure that our colleagues who are responsible for like the face to the customer, the sales organizations and so on, marketing organizations, product development organizations, that they make use of this information afterwards also to in the terms possible to learn from that and to adapt, for example, like their offer or their reactions or whatever. Yeah, and is it used in the capacity management? I think was the next, the second question. Yeah, I think it's of course we see what's happening currently, and then we see where's demand and so on. But of course, currently we don't can make use of this in terms of like making new schedules or whatever, because this is merely not possible. Yeah.
Okay. So thanks, Annika. Now we have 2 questions for Valentin, I think. So let's do this. Valentin, do you have a backup system in case the satellite system collapses due to orbit dangers?
Well, so the question, I'm not sure if the question addresses the Galileo and GPS satellites or if it addresses the Egnos satellites. So regarding the Egnos satellites, well, there are several satellites online. So if one falls down, the other one can take can take the relay. If it's related to the Galileo and GPS satellites, it's very unlikely to have a full system failure of this constellation, as we will still have anyway other satellites. I mean, not all the satellites will fall down, so we'll still have satellites on the sky so that we can use to obtain our position on Earth. But there are engineering rules that have been used and that are in place for the use of these satellites that are handled by USPA and ESA. So to have to summarize, to have a full failure of the constellation is very unlikely for the Galileo, and for the Egnos there are other satellites on which we can rely on top of the fact that we also would like to have for Egnos a ground service that we could use in the future, as the SBAS satellites are not fully fitted for rail applications.
Okay, so thanks for that. And another question for you. what is SEAL and how is safety level for aviation compares to railway? Rough numbers are helpful.
Yes, so SEAL means safety integrity level. This is the level that are used in railway. SEAL 4 means actually 10 to the power minus 9 error per hour. So it's a very low level. It's not that easy to compare straight with aviation, but let's say that in aviation we have an error related to 10 to the power minus 7 per hour. So it's about 100 times more higher in railway than in aviation globally. That's what we can say so far, with also the fact that our environment is much more complex than what is there for aviation.
Okay, thanks, Valentin. So we have a last question for Daniel again. Is there a web page where we can find more information about the different calls being planned?
Yes, it is indeed. I hope that you can still hear me.
Yes, we hear you.
It seems that my camera was a little bit frozen. It's actually www.euspa.europa.eu. It's our website, the website of the agency, and there you can see all the opportunities that are at the present opened. And if you search for the agency work program, there you even see the longer term planning for what concerns the calls. So again, this particular call can be found in the work program, and it will be published on our website once it's becoming actual, which is going to be in autumn of this year. I hope it helps. Thank you.
Thank you, Daniel. So thank you all for answering the question, and also to the participants for all the questions you've sent to us. And I think I hand over to Florian now.
Thank you, Yasmin, for answering those questions and all of the guests. I think that gave very good insight into the first presentations and also the general project. And to all the audience, please feel free to add questions for the next presentations at any time during the presentations and vote on your favorite questions, as we will have a next Q&A session before the lunch break. So after this first morning, with the overall insight of the CLUG project, let's dive very deep into the fundamental points of this project now. So, what are the mission requirements? What are the stakeholders and the needs? All this are topics of the work package 2 of the CLUG project, as you have seen. We want to answer, what does the localization system need to fulfill? And how do we translate those into the system requirements and architecture? For this topic of the localization needs and the system requirements, I'm very pleased to welcome Muthu Kumar from Deutsche Bahn. Muthu is the technical project manager of the CLUG project at DB and also a system architect at Deutsche Bahn. Welcome, Muthu.
Thanks, Florian, and thanks for the welcome. Let me share my screen. So I hope you see my screen now. Florian, do you see my screen?
Yes.
Okay, perfect. Okay, then welcome everyone, and a very good morning to all of you. First of all, thank you for taking the time to be here and to learn more about the CLUG project and the work of the consortium over the last 30 months. So as Valentin already mentioned, we are a very broad consortium with 10 companies, and a lot of work was done to define the localization needs of the railways and the system requirements. This was the main focus of the work package 2, and it's a pleasure for me to be able to present this today to all of you and to explain not only what needs we identified, but also to give you an overview of the methodology that we followed in this project. So first things first, you already heard about our effort to bring the ERTMS and ETCS train localization system to a new era by using an innovative multi-sensor fusion approach where GNSS and digital maps together with other sensors play a key role. And it's important to remember that on one side, it's the technological innovation, and on the other side, it has to fulfill a lot of different needs. And we see localization in the railways as a key enabler for a few different digitalized concepts, including intelligent traffic management, automated train operations, whether that's automation level 2 or 4, and also moving block operations. In addition, we believe that the new localization system can provide a better operational quality through an improved performance, while also decreasing the capital expenditure and the operational expenditure of field elements that are needed for localization. Last but not least, this project also focused on providing a first set of standardized interfaces that can then enable the modularization of the ETCS onboard. You will hear more about that from Sebastian's presentation after mine. Okay, before I get into the work that was done, just to give you a quick overview of the work package logic and the scope of my presentation. So I'm mainly focusing on mission definition and the high-level system definition, meaning the high-level needs of the railways that we identified in work package 2.1 and the operational scenarios, meaning the environmental conditions and the situations in which the localization system has to perform. Based on this, then we derived the high-level system requirements in work package 2.3, and we did the preliminary safety analysis to identify the safety targets, the so-called SIL targets that Valentin also explained during the Q&A session. All of this together was then published as a public deliverable as part of work package 5, where we have published the preliminary definition of the system performance, including the interfaces and the requirements. Okay. When we talk about requirements, when we talk about stakeholders, we need to remember that there are three main stakeholders involved. On one side, you have the railway undertakings and the railway infrastructure managers, and on the other sides, you have the passengers. When we talk about passengers, it's important to remember that the passengers are interested in localization information that makes their lives easier. So they are interested in knowing, is my train on time? Will I be able to get my connecting train? On which platform is my train arriving at? These are the key informations that they are interested in. And therefore, any localization system that we design has to be able to provide the train position information in a real-time manner and also in a frequent manner that we can enable such comfort applications. However, the biggest part of the work that we've done in this project and in this work package specifically was in terms of identifying the needs of the railways itself. Fundamentally, the railways need to know the location of the train and other dynamic parameters to ensure that the train can travel from A to B in a safe and cost-effective way. Annika highlighted during her welcome address a couple of different drivers behind it. It's important to remember when we speak about the needs of the European railway operators and undertakings, there are a few key drivers. On one hand, you have the need to increase the capacity without building additional infrastructure or tracks. Then we have the need to increase the reliability of the service, especially in the German context. And then we would also like to improve the efficiency of the service, and while decreasing the operational and the capital expenditure required for the service in the first place. We are also interested in enabling innovation and digitalization, as these are key drivers for the future digitalized railways in Europe. Therefore, any future localization system has to enable all of these different applications and has to enable all of the different stakeholder needs. Do I mean by that all of the high-level needs are the same across the different stakeholders? As you can imagine, railways are a complex operation. There are several systems involved here. Take, for example, traffic management. Traffic management basically plans the movement of the train, whereas train control sets and secures the route of the train so that there are no accidents. Train protection, on the other hand, ensures that the train always stays within the safety envelope that it was given. And then as we move towards the vehicle, you have applications of systems like ATO, which essentially drive the train and, depending upon the grade of automation, also execute other functions in the train that are currently handled by the driver. It's important to remember each of these different systems have a unique need towards the localization system. It might differ in terms of the accuracy they need, in terms of the safety level that they need for the information that the localization provides, or even simply the frequency of the update in terms of the localization system. So the approach that we took here in order to identify these needs was, rather than trying to fix the problems that we've already identified and that we are already aware of, we choose to have an approach of thinking about the future railway architecture and then to derive the requirements for the localization based on the needs of this European future railway architecture. As you probably would have already understood by now, railways are increasingly becoming more and more digitalized, and any future localization system has to therefore enable this digitalization and should not come in the way of the digitalization. It's not just about fixing the reliability issues of the odometer that we are already aware of, but it's about analyzing what kind of needs do we have in the railways, maybe even 5, 10, 15 years from now, when we think about how automation is going to work and how railways are going to be shaped in the future. Therefore, when we approach the problem, we try to take a holistic approach that takes all of these needs together. And the approach that we therefore followed is called this wider system of interest approach, which is basically a 3-step approach. In the first step, what we did was to identify the systems and the functions in the railway architecture that require localization information. It doesn't matter what kind of localization information, the importance here is placed on localization information is needed for these systems to fulfill their own functionality. This was the first step, regardless of whether it was a trackside system or an onboard system. The second step was to identify the kind of localization system that is needed. For example, if you take a futuristic system like incident management and prevention, which has different functions, but one of the main functions is to obstacle detection, then it would need a 3D position of the train rather than only the 1D position of the train, which is currently used. So this was the second step that we did. We identified the different kind of localization information that is needed by the different functions. And in the third step, we identified the quality of the localization system information that is needed. So in terms of non-functional requirements, in terms of the safety levels, in terms of the frequency, in terms of the accuracy needed, and so on. So this was the holistic approach that we followed. This was the 3-step approach that we followed. This approach and the way we worked, we used a lot of the existing information, and we also improved and contributed back. I will get back to that later, based on the work that was already done in other European initiatives, including RCA, Cura, Shift to Rail, and so on. This wasn't the only way we approached writing the high-level needs of the railways. Another one was to think about how do we specify the high-level needs in a technology-agnostic way as much as possible. So this approach was necessary if we were to successfully digitize the railway operations and to build it in a future-proof way as much as possible. One really good example here would be the use of digital maps as a kind of reference points to identify the location of the train, rather than using the location of the physical infrastructure elements like we do today with Eurobalises. Of course, this approach involved a lot of brainstorming, discussions with the stakeholders, and close collaboration between the 3 railway operators and infrastructure managers in the project, my colleagues from SNCF and SBB and DB, and also supported very actively by our industry partners in the project, CAF and Siemens, who have a lot of railway knowledge themselves. So it was a very good consortium of railway undertakings, infrastructure managers, and railway companies who have knowledge about this. So this was one way in which we try to build requirements in a future-proof way. So this is what we did in terms of the mission requirements. And then if we now remember the slide from earlier, work package 2.2 was on operational scenarios. What we did here was, in addition to what we've already done in terms of identifying the needs, we looked at what are the different conditions in the railways in which the localization system has to operate. One of the most famous examples that most of us can think about when we think about GNSS is that it does not work in tunnels because there are no signals and the signals are blocked. So there are several different environmental conditions that impact any localization system in the railways in a special way or a unique way compared to aviation. So that was one half of what we did. And on the other half, we also took situations and operations in the railways that are unique and that might have an impact on the localization system design and the requirements. So together with the mission requirements and the operation scenarios, the outcome of the high-level mission definition, then we derive the system requirements for the localization system. I don't want to bore you with a lot of requirements and a lot of numbers. I will basically try to focus on two key examples so that you understand the methodology we followed. One of the most important targets that the European railways have is to increase the capacity. At DB, we've made an analysis on a specific line where we would like to run 33 trains per hour. And as you can imagine, this is already quite a challenging target. And in order to achieve this, the operational headway analysis that we did, meaning the spacing between two trains when we are moving them in a moving block way, was very small. And therefore, it automatically means that the localization accuracy has to be high or the odometry inaccuracy has to be very low so that the safety envelope is actually quite small. And therefore, the analysis told us that the safety envelope or the odometry inaccuracy has to be a maximum of 1 second in order for us to reach the capacity target. This then enabled us in this innovation and research project to define a speed-dependent localization accuracy. This is different from what is currently in TSI. We're aware of it. We are already working on studies to compare the two different localization accuracy requirements we defined and how this might be able to be translated into the TSI. Another example of how high-level needs were translated into system requirements is this futuristic system where we have to detect obstacles. Currently, the odometry system only provides a one-dimensional position. And as we move along the automation grade, we know that the system needs to have its 3D position in a global coordinate system and even the heading angle so that it can accurately allocate objects to the different zones. So this was also another system requirement that we took into consideration. I mentioned during the wider scope of interest that we benefited a lot and we also contributed back to European initiatives. So this slide gives you an overview of where CLUG contributed and where CLUG benefited from. The mission requirements of CLUG, the first starting point or the seed for the discussions was the work that was already done by the ERTMS user group and also to a certain extent that was discussed by the different European railway undertakings and operators. So we've used that as a seed point to derive the mission requirements and the system requirements, and we've also contributed back to the ERTMS user group, similarly to RCA and OCORA to further work on the system requirements there in these two European initiatives. In terms of shift to rail, we've contributed by defining and providing the operational scenarios that we defined in this project. And this has been then used for the demonstrators and to further refine the test plan and so on that we've done there. Right. So in the interest of time, there's a lot of information available in the public deliverables that we've already published. So you can already read on our website the high-level mission requirements definition, which is the outcome of the work package 2.1 and the outcome of work package 2.2, which is then the operational scenarios. These are already published since last year and they are available on our website. The outcome of the system requirements are currently under review by USPA. This is the outcome of work package 5.7, and this will then be published in the coming weeks or perhaps in a month or so. So with this, I thank you for your attention, and if you have any questions, then feel free to put them in the chat. So I hand over to Florian.
Great, thank you very much, Mutu. I think you and the entire team and all the colleagues working on those topics and deliverables can be very proud of the results and all the amount and results, amount of work you have put into this. And I also really recommend to look into the public deliverables on the website, download and read through them for a deeper insights. After the localization, user needs and requirements, let's carry on and look at the work that has been done regarding the infrastructure and the interfaces towards the fail-safe train localization onboard unit. And for this topic, I welcome Sebastian Ohrendorf-Weiss from SBB. Sebastian is the CLUG Technical Project Manager at the Swiss Federal Railways. And welcome, Sebastian. The floor is yours.
Thank you, Florian. I hope you can see my slide now. And first, I would like to give you some figures. We have talked about the localization function, which is today done on trackside, which should be performed on the onboard side. So in Switzerland, we have about 32,000 trackside train detection systems on the track, which are cabled to the RBCs. And then on the other side, we have 3,200 onboard units. So it's the factor 10 if we talk about shifting the localization from today's system to the onboard for the safety part. We have heard that this is quite a challenge. And we have also another challenge, which is regarding the cost of the ETCS onboard unit. And this is why we say we need the modularization of the ETCS onboard unit. So where are we today? Today, we have one monolithic ETCS onboard unit, and there's one certification process of the whole unit. So the train localization function is kind of hidden within this onboard unit. And therefore, if you want to change anything there, you have to recertify the whole unit. Our big challenge, since we have a big fleet, is the migration path. How can we migrate a function that is within a monolithic unit in the future? Because we want, first of all, to bring in new technology and also make the system upgradable. So we, in the project, decided that we want a train localization onboard unit of the generation X. So we will design it, and then we have to standardize the interface to the ETCS onboard unit. This, in case we want to replace the generation X by a generation Y, we can do because the interfaces are standardized and open. So this is a way we can think of future migration, which is not possible today. The huge advantage of this is that you only have to certify the train localization onboard unit itself without recertification of the whole unit. So we focused on the standard of the interfaces, and this is what I will show you now. Today, we talk about the architecture. So we have different sensors on the train, like police readers, which are in place today, the tachometer, and the system of interest will also be explained later by Arno. Therefore, I focus now on the external interfaces of this system. There, first of all, we have the police reader, which is giving us an interface to the train localization onboard unit because it's existing on the train. So this is information acquired from the ground. Then we have information through future rail communication. Here we say 5G. And there we assume that we will have Egnos ground dissemination and digital map transfer for the train localization onboard unit. The third, we have signals direct coming from space. We think of GNSS as a source. So Galileo, Egnos, satellites, and GPS. And then last but not least, we have the output, which we want to standardize for safe and non-safe user applications. And this I will show you now on the following slide. So I told you that we have to definitely standardize the interface to the train ETCS onboard unit, but there are also other user applications which we thought of in CLUG. So there we decided this is localization report 1 because this is already existing today. Then we defined other localization reports 2 to 4 for other applications which are safe and non-safe. For example, passenger information system, the ATO, the incident management and perception, and others you can think of. So in total, I will give you a brief overview of the 4 different localization reports we defined. They all have a need of train position, velocity, acceleration, and confidence interval, and the formerly mentioned safety profiles, which are here categorized in seal level 0 to seal 4. So localization report 1, we require a 1D position as it is used today with a seal 4 level and the output rate of 200 milliseconds. This is thought to be input to the ETCS onboard unit for train position report generation, information on the DMI to the train driver, and the supervision of the braking curve. Localization report 2 is also a 1D position, but there we have a lower sea level, which could be used for train control, management system, and ATO stopping at a platform without a train driver. Localization report 3 is even a CL0 output, but at a higher rate. For example, ATO with a train driver, or in Switzerland, we have problems with our pantograph positioning. These are use cases for localization report 3. At the end, we also have a 3D position localization report we defined at the output rate of 30 milliseconds for passenger information systems, driver advisory systems, etc. So coming back to the introduction, I told you that we have a factor 10 between trackside train detection systems in place today and the onboard units. I want to summarize the main factors why we need a standardization and modularization of the onboard unit. First of all, today we have many systems which provide localization information for the passengers platform, for the EBC. So in the future, we only want to have a single source, which also makes the onboard system cheaper because it has only to be calculated once. Then we want a separation of the train localization onboard unit, for which provides the function to locate safely and reliable train in its orientation on the track. We also want this modularization to leverage new localization technologies without the need to recertify the remaining part of the ETCS onboard unit. And last but not least, we want to update the train localization onboard unit independently from the remaining part of the ETCS onboard unit. So if you have any questions, please put them in the chat.
Yeah, thank you very much, Sebastian, for this interesting presentation. And I think we are all looking forward to the questions. So let's move on. Let's focus on the localization system design next. And for this topic, we have invited 2 experts of the CLUG project who will present it. Please welcome with me Arnold Sver from Airbus. Arnold is the CLUG design work package leader at Airbus Defence and Space and the lead of a solution A in the project. And Michael Jüttner from Naventic. Michael is the Chief Operating Officer at Naventic and also the lead of the solution B. So the stage is yours.
Hi, hello everybody. Could you hear me and could you see
Yes.
the sharing? Okay, super. So yes, I'm will present the localization system design that we did on CLUG. So in this first slide, here are recalled the main targets driving the functional design. of the CLUG TLOBU. TLOBU stands for the Train on Board Unit. So it has to be designed for the ERTMS level 2 and 3, so preparing the autonomous drive of the train and to be compatible to the entire European railway networks. This is the main objective, of course. Then CLUG is fostering the transition from trackside-centric to train-centric localization. So it moves the way to compute the localization on the train systems. Then the next objective that also was mentioned before is the trackside equipment for the localization shall to be reduced as much as possible. And then, of course, the design shall be safety of life. So it shall output localization data that have to be safe and with integrity. So from the full system localization diagram, still the same diagrams that we are sharing during all the days. And from the external interface that was described by Sebastian just before, we are now focusing inside this perimeter, so into the TLOBU perimeters. Assuming the train already knows on which track it is, so this is here a way to explain some parts about the positions. So we are assuming here that the train already knows where it is, and there is a dedicated function described better, but here I recall that the train needs continuous absolute position, speed, and accelerations. So I will try to just recall some things that seems to be easy, how these parameters are computable. So first, physics allows to compute the distance, speed, and acceleration versus time by several ways. So natively, I would say, if we are here at the distance levels, for instance, or via derivate computations that we are here, or integral ones. But for the integral computations, the things that is to be recalled and important, of course, the integral does not offer the absolute part. That is to say, the initial or reference value is not accessible from integral computations. In the current rail systems, the along track parameter is not requested for safe user applications. So we have only these two parts. And then along track position and speed. So this distance and speed are computed by two systems currently. So the trackside balises with a reader on board the train and the track and the balises on the infrastructure, and then the odometer systems being on board. For positions, the balises natively provide the absolute position, but not continuously, because there are regularly some balises to be crossed, but not continuously. And so this is the odometer system that will provide that provide continuously the relative positions, and both complete the expectation to be continuous and absolute, and of course with the accurate and safety level that is requested. For speed, the odometer systems offer natively the continuous and absolute speed. For the future, acceleration has to be also provided with safety and integrity like position and speed. Even if the functional architecture is not perfectly reflected by my coming explanations due to the use of data fusion techniques, I'm trying here to just highlight the interest of the sensor types that we defined in CLUG. For positions, GNSS and SBAS natively provide the absolute position, but not continuously due to RF masking, so similarly to the current balises. Potentially, some few balises could be also considered in critical area depending on too poor GNSS access and IMU sustainability capacity in time and in distance. So it depends on the area. For the IMU, it means that we take into account that the internal drift that may involve to add some few balises. Speed sensor and then IMU most priorly here is providing the continuous position, but relative. And it's done by integral computations. Then for speed, the speed sensor, typically a tachometer, provide natively and continuously the absolute speed. But for safety reasons, so that's why it's in gray here, the GNSS S-bus by derivates offers the absolute velocity, even non-continuously with the safety and integrity. And the IMU is providing by integrations continuously the relative velocity. And then for the acceleration, sorry, the IMU natively offers continuously the absolute acceleration with safety and integrity. So even supported by the speed sensor via the derivate here. So to summarize, GNSS S-bus natively provides the position domain. Speed sensor provides natively the speed domain, but without safety levels, because here we are using just a part of the odometer, let's say. Currently, odometer is using several speed sensors. Here we only use the speed sensors. But S-bus and IMU via derivative and integral provide the speed parts. And then the IMU continuously provides the accelerations. These sensors are complementary for tight coupling fusion techniques using Kalman filters because they reduce the temporal and calibration bias. Here are recalled the outputs required in safe and with integrity by CLUG. In blue, there is small differences from the current things. Last reference points that could still be a balise, like the current system. But here it's more a characteristic point of the track. That could be a switch point, specific start of a track edge that is freely defined by the railway operators and set into the digital map. So without associated trackside equipment like it is done for the balises. And then a long track acceleration in 1D is also requested. So all the safe localization data are in one dimension here. So this is the output from the TLOBU for the safety parts. And of course, all other localization parameters, such as 3 dimensions, position, velocity, and time, or attitudes, are output, but are not needed at the safety critical level. Here is illustrated the different allocation of safety to the TLOBU. So safety critical levels stand for DALB in aviation's domain and could be compared or similar, but not equivalent to SIL3 in railway. And so this safety critical level in orange is ensured by Egnos part that is disseminated from ground or also potentially from space. Here the name of the unit that deals with that is data unit and not receiver because it is not asked to provide a classical PVT, but only the safe and augmented measurement from GNSS, Galileo and GPS. So this equipment is dedicated to train and it has to be developed under the same safety critical level as Egnos, but here in a railway domain, not in aviation. Then we have the IMU that is requested in safety critical level also for several reasons. One of them is because the acceleration is now requested safe compared to the current system. And the IMU provides natively acceleration and inertial data. Another reason is several IMU certifiable currently in DALB for aviation. They are available on the market, but not yet in nor in SIL3 or neither in SIL4 for rail. So these IMU available in the market are good starting points for their use in a rail, and the IMU technology are still improving so fast that the effort is made on them. Then we have also the digital map function, providing the ground truth. Is it also at the same safety level as the GNSS data, safely augmented by Egnos and as the IMU data. And then we have several data fault detection and exclusions that are not represented here because they are spread at several locations into the TLBU. So the fusion, navigation, and integrity algorithms, here, have the roles to output the navigation data with their confidence intervals in the safety catastrophic levels that stand for the C4. We have designed two solutions. One solution that is named Solution A is led by Airbus. This solution architecture in terms of functional architecture is driven by the safety requirements, as well as targeting the technical and full compliance to them. And another solution named Solution B, led by Navantic, is focusing, is targeting a disruptive adaptation of their current existing product to be derived to the railway context, and it does not cover all the requested perimeters. So some functions that was studied in Solution A are reused. What is common to both solutions? We have the same set of sensors, so as explained before. We have the same TLW safe requested outputs, so with their integrity, so ensured by the safe confidence intervals. Same similar strategy with regard to the fusions and tight coupling using Kalman filters. And then, as we were saying, we provide the unsafe data that could be used for unsafe applications. Common main features here. So we have the digital track map in 3D that includes the reference points and that enables also the track selectivity. Then we have the set of the sensors. Egnos data continuity is ensured by ground disseminations and by signal in space, sorry. Can I go back? I don't know. I was there, yes. Speed sensor is not to be confused with the current SIL4 odometer systems. So that's why I tried to have a different wording for them. Then we have the navigation engine that contains several functions, start of missions or initializations, trackage determinations, that is also named track selectivity, the along track position, speed and accelerations. Then we have the data FD, so fault detection and exclusions to ensure the requested safety quality of the data to be processed. So there are some at sensor output levels, but also at system levels, so fusions levels to compare each of them. So the data fault detection and exclusion function are part of the integrity functions. Sorry. And then the integrity engine that is here is computing the confidence intervals for speed, for position, speed, accelerations, and also confidence status for track selectivity and other integrity data. Here are represented the perimeter per solution, so the one by Airbus and the one by Navantic, concentrated at that place. And let's start with the solution A. Now, let's describe each functions deeper in the solution A. So, in the fusions and initialization and start of mission, this function was not deeper analyzed and defined in CLUG because several technicals or operationals and /or maintenance concepts are conceivable. This function is assumed to output the initial localization parameters, including the initial track on which the train is. Then, still in fusions, and already mentioned before, we have the GNSS and SBAS and GNSS local error data fault detection and exclusions that are fusions to output safe and filtered pseudo-range, Doppler range, satellite positions data and constellation time, but not PVT. Then we have the fusion track selectivity. This function outputs the current track part on which the train is in real time. It also provides confident indicators for the safe confidence status computations. Then we have the fusion localization. From all filtered input, the localization function perform IMU plus 3D track map matching. It is done at high rate level, so up to 100 Hz, for instance. Then the IMU plus 3D localization solution is aligned in absolute by the GNSS and SBAS at lower rate, of course, and also I would say 1 Hz natively, but because of RF masking event, it could be a long duration between. It detects the reference point transition when crossing a map with a track selectivity point from the digital map. And then it outputs the safe track edge ID, so the track edge name on which the train is, 1 dimension along track position, speed and attitudes, and unsafe other 3 dimensions parameters. And also it produces delta in position, speed, acceleration for the integrated data computations, so to that modules. And here, the integrity and confidence interval computation, this function computes the confidence interval with integrity, so separately to the other one. Here, this is a list of the safe and non-safe data that are displayed, still trying to highlight with the colors the safety levels, but it's clearly an illustration here. And so on one hand, we have the estimated position, and on the other one, we have the confidence intervals or status. So what are the main outcomes for the solution A led by Airbus? So we reached the following technology readiness levels. So for the sensors, they are at high levels and demonstrated in relevant environment thanks to the Work Package 4 test that will be presented later. Of course, because this sensor already exists. For the digital map, the technology is validated in lab, so we did some map matching, and also you will see some results on that. For the along track and map matching functions, so the one that provide the estimated along track position, speed, and acceleration, the technology was validated in relevant environment in the sense that it has been prototyped with replay real data, the same, it will be presented later. And for the other one, so data fault detection and exclusions, data units for GNSS and Egnos, start of missions, track selectivity, integrity, confidence intervals and status. We are between the TRL 2 and 4. So as a technology concept or proof of concept, some part have been validated in lab. And let's say that the critical items with regard to the proof of concept target of CLUGs of this run has been done. So this rich TRL enables the first simulated safety performances that will be presented later by Pierrick, and some experimentation with real data. So without integrity, clearly, because using these prototype functions. Now we wish to increase the TRL level, in particular on the track selectivity algorithm, and on the data fault detection and exclusion functions, and of course on the integrity algorithm for future prototyping. So to increase that part clearly. Now I give the floor to Michael for the solution B. Michael, could you hear me?
Yes, thank you, Arno. I can hear you. So okay.
So I stop sharing it, and then you take the hand.
Yes, I will. Okay.
That's fine. Yes, you can continue.
Okay, thank you. So I'm continuing now with solution B. So solution B is an adaptation of Naventics automotive products to the rail context, and it covers, as Arno said already, a subset of the CLUG railway train localization architecture as shown before. The main difference here is that solution B implements a GNSS unit as software-defined GNSS receiver. With the software approach, the hardware can be minimized to a simple RF front end that does the down conversion and digitizes the antenna signal. satellite acquisition, the signal tracking, the generation of the observables is done in software for the constellations GPS and Galileo. And the hardware acceleration, by the way, is done with the use of graphic processing units. So then there's the navigation engine, which is in charge of collecting the GNSS observables and the sensor data from the sensor layer. Solution B's navigation engine processes IMU data only. Here, the target architecture for non-safety critical platform is sketched. Solution B approach follows the principle that integrity can only be achieved by implementing a continuous, traceable and unbroken chain of integrity, starting from the RF stage over the measurement engine to the navigation engine. The functional B design focus is on adding integrity on the GNSS RA measurements produced by the software-defined radio, here outlined as data FDE. And the solution B design focus is also on the tightly coupled sensor fusion. All mechanisms that aim to detect to exclude errors in the GNSS baseband processing, so in the GNSS sensor, are combined in an integrity and safety layer. This layer collects signal and receiver matrix that include quality estimators from the GNSS sensor stack. Based on an hazard and risk analysis, algorithms were developed, or at least concepts were formulated to detect and mitigate feared events, here called as monitors. Each of these monitors calculates internally risk estimates, which are delivered to a central control logic, shown here. In its simplest form, the control logic can be represented as a weighted sum of integrity risk inputs followed by some activation function. It decides which observables shall be passed to the navigation engine or which are shall be discarded. It's also capable, as with the control logic, is also capable for switching the receiver into a safe state within a fault-tolerant time when the overall receiver integrity appears to be compromised. So the safe GNSS data acts as input for the navigation engine, which implements further integrity concepts with the aim of generating safe navigation data. These topics are partially handled by Solution A. The Solution B approach features a built-in integrity checking for safety critical systems on GNSS baseband level, and it can be used for non-safety critical precise positioning applications, of course. Now I'd like to briefly present the main outcomes of Solution B. So the use of the GNSS software unit, the software defined radio, was illuminated theoretical and demonstrated practically in the CLUG project. Techniques for fault detection and exclusion, especially ARAM for the GNSS unit, were developed and partially implemented as prototypes. And in addition to the software radio, a tightly coupled sensor fusion was also used in the field. In summary, a certain maturity could be reached for Solution B, and prototyped algorithms could be tested in work package 4 on the train domino. Concluding can be said that for guidance systems in autonomous railway applications, the GNSS sensor must be completed by safety information and integrity guarantees. With the CLUG project and Solution B, a technology concept was formulated and partially prototyped to get one step closer to the safe positioning based on satellite navigation. So I'd like to thank you for your attention, and I think now it's the Q&A session, right?
Yes, that's right. So thank you very much to both of you, Michael and Arnaud. So now it's time for our Q&A session. And let's have a look at the question you have sent to us. I think this time we have quite a lot of questions. So let's start with Mutu and the questions for you. So the first one is, what about real-time localization and shunting modus? By when is the solution to be expected?
So in terms of real-time localization for shunting, of course, it was one of the different operational scenarios that we identified as an input for us to derive the system requirements in 2.2. There are two key modules that were not in the scope of CLUG currently. One was start of mission or the system initialization in general, and the other one was track selectivity. So you will hear more about the long-term roadmap that we've developed and when we think products might be available later in the second half of today, when the presentation during Dirk. So I mean, I think it will take at least a couple of more years before we can think and talk about products.
Okay, thanks, Mutu. So next one is also for you. How do you verify the correctness of the digital maps in use?
How do you verify the correctness of the digital map in use? That's a good question. And in the scope of the CLUG project, the main focus was on defining the digital map format on the air gap between the train and the trackside. And this is the focus of the presentation by my colleague Henning Nitschke, who will present, I think, after the break. So it was not the scope for us to develop a detailed digital map data management process and validation process, and ensuring that it's always up to date and ensuring that it has the safety levels that is needed for localization and other onboard applications, which is a huge topic in itself. So keep that in mind. So this will be taken care by a data management process, which was not in the scope of our innovation project.
Okay, thank you. So next one also for you, localization can definitely be an enabler for future railways, but with so many stakeholders and a complex 24/7 operating system, how is the transition possible?
The three key railway undertakings and operators, so SNCF, TB and SBB, we have our own internal strategies and roadmaps for the rollout of ETCS and for the migration plans. So this very much depends on the migration plans of the different undertakings and the operators, but this is already something that's part of all the conversations and part of the considerations that we have in terms of how we will roll it out. And this is why also modularization of the onboard system and onboard ETCS, which Sebastian presented, plays an important role, because for some systems, the technological roadmap or lifespan is much shorter than for other systems. So by decoupling it, it also makes our rollout and migration plans a bit more easier.
Okay, so thanks, Mutu. And now we have questions for Sebastian, I think. So let's start with the first one. Where are the XXMS output rates coming from?
Yeah, thank you, Yasmin. The output rates are coming from the assumption today we have, at least in Switzerland, 6 seconds for a train position report to be sent to trackside. In the future, we need at least 1 second. And therefore, we say we need a much higher resolution. And this is how we came to 200 milliseconds for the CL4 output. You see the lower the safety level is, the higher the output rate, because you don't have to do the integrity check. This is how the numbers were derived.
Okay, thanks. So next one also for you. What is the delay from the time the localization information is measured until it is made available as a report in the output interface?
Well, there we have to say in the CLUG project, we did a post-processing. So we didn't do a live demonstration yet, and therefore this answer cannot be answered. It can only be said today there is 1 second for the EVC to generate the train position report, but it does not. It's not specified when the sensor data was acquired.
Okay, so Sebastian, please clarify, why do you need 1D position messages with low seal when you already have those seal 4?
Well, also there we try to be generic and cover all the different applications, because it could be thinkable that in a first stage of products, there's only a CL2 level reached. Therefore, we showed all the different CL levels that from our point of view are thinkable.
Okay. And I guess the last one for you, the TSI 2022 will introduce an onboard modularity and standardized interfaces of the ETCS onboard with the train. Is CLUG requirements are aligned with?
We are in the CLUG project in close contact also with ERA, and the modularization is a topic for the next TSI regarding the train localization onboard unit. So it's not coming with the current TSI.
Okay, so thanks, Sebastian. And let's go on with the question for Valentin. Regarding the IMU, are the accuracy and performance specs requirements already defined, or is this up to every train operator? Valentin?
Maybe I could answer.
Yes.
Arnaud Sfer speaking. The accuracy and performance specs are not required by the, let's say, work package 2, so from the railway operator, but more from the functional architecture things. And then we are not specifying specifically a type of IMU, but several have been considered in terms of grade. And this afternoon, you will have a presentation of some results. And these results, are using several different type of IMUs. So they are not compared in the presentation, but I'm saying that finally the IMU specification is more a requirement from the functional architecture side more than the operator side.
Okay. Thanks. And maybe Valentin, you are back. So another question that you could answer, does safety critical means SIL 2 and safety catastrophic SIL 4?
I can also answer.
Okay.
It's more because it was about my presentation, and then as let's say DAL and DAL in aviation and SIL in train has no equivalence. It is more simple to express it at a qualitative safety level. So here in the presentation I did, critical safety level stands for DAL B in aviation and more in SIL 3 for railways, and catastrophic is DAL A in aviation, but SIL 4 in train. But once again, there is no equivalence between, but their tolerable hazard rates are similar, and then this is why we try to illustrate this with the color.
Okay, so thanks for this answer. And now we have a question for Arnaud and Michael. Are also GPS signals used as well as GNSS and Egnos to provide safe localization?
So maybe I missed. The answer is if we use a GPS signal inside the TLOBU, the answer is yes. In fact, when we mention GNSS, we stand for GPS and Galileo. And then for Egnos, we are in CLUG, we were focusing on Egnos DFMC, so DFMC using GPS and Galileo. Okay. If I understand well the question.
So, yeah, otherwise you could
there will be another one.
Yeah, I think so.
Okay.
Okay. So, and next one is what do you mean with balises provide absolute positions, since this is not the case in ETCS right now?
I can try to answer if I understand well the question, but maybe Valentin or Pierrick or Bernard or Mewtwo could answer. When I was saying absolute position, it means that the balises, the position on the track are well known in absolute part. And when a train is crossing a trackside balise, so the balise reader inside the train knows that is the starting point in absolute. And then the relative distance from that balise, that is a reference point locally into the train, is then computed, the distance is computed from the odometer system. Mewtwo, or if you want to complete, if I understand well, what is the sense of this question?
Just to add, Arnaud mentioned the absolute position is created only in combination with that map. Or the digital maps, which also includes the 3D position of all the balises that are installed. So
yes, sure.
Yes, the person who asked the question is right. The balises do not themselves provide a 3D position or their absolute coordinates. This is then the job of the digital map.
You should be right to the question. I was not understanding it well.
Okay.
So
So
another one is for me, tachometer classified as no
Yes.
safety level mean basic integrity or no integrity
Mhm.
is required at all. Yes, in fact, the CLUG is not intending to reuse an odometer system safety at SIL 4. And so here, because we have on one side on position parts, we have already safety access. And then from the IMU also, then we don't need safety levels with regard to the speed parts, the speed sensor. So a tachometer is well adapted without any safety levels or any basic integrity at the time of this proof of concept levels.
Okay.
In other words, there is no added values getting some integrity on it.
Okay. So, and are the mentioned solutions A and B, Airbus and Aventic, as well used as APIs? And how is the safety relevance regarding communicated data between the systems defined towards those API systems?
I would say it is more a system question here.
Okay.
Let me understand what it means. I don't understand if it's relative to the way the data are exchanged between the functions.
Maybe if the function
Maybe.
calls. Also.
I could also try to answer it.
Yes.
Essentially, the safety levels of the communication data between the systems is also given by the SIL integrity level of the information which Sebastian presented. So if you have a 1D position that is required at SIL 4, then the communication channel between the systems that communicate this information is also expected to be SIL 4. Of course, it depends on the onboard architecture and the communication design and so on, but essentially you could assume it to be this. I hope this answers the question.
Okay, thanks, Mutu. Another question, I think also for Arnaud, what error margin is expected for the measurement of position, speed and acceleration at the output of the sensor fusion algorithm?
I would say that error margin is not the proper word. You will see later in the presentation from Pierrick that because we are in safety request, the point is to provide confidence intervals of the estimated position, and the real position should be inside these confidence intervals. And this confidence interval has to be computed under the expected safety level. So it's not a question of what is the accuracy or error of the estimated position, speed, or acceleration, but more on the computation of this confidence interval. So there is no, let's say, tight accuracy request, but if we want to provide an available system in terms of safety, then the computed confidence interval has to be below the expected one, and it will be presented later.
Okay. And another one, do you use a rail vehicle model and tracks constraints to help the ENS? Are you able to detect a stop of the train?
Maybe Michael should answer this, but on Airbus side, we don't use any vehicle models. The map matching is done as a fusion parts. So yes, it is firstly led by IMU plus digital map matching.
And also now for solution B in this project, it was not implemented a special train vehicle model, but of course it belongs or is necessary if the fusion is in a later stage.
And then for the rest of the question, are you able to detect the stop of the train? Yes, of course, it is needed, but still the same answers within the specified confidence intervals that is needed. So for the speed, there is also a confidence interval for that, and then for the standstill, it's another question that will be more complicated to answer that there. And
Okay.
after, how do you combine RM with Egnos? It's more a question to Michael. the last
Okay, I can read it out if you want, so the audience hears it again.
Yes.
How do you combine ARIME with Egnos? In addition, both concepts do not protect against faults from local effects, which are present in aviation domain. So therefore, how do you address this issue?
For solution B, Egnos is not implemented. It was a subset of this whole solution in CLUG. And I know there are investigations going on to extend Egnos to the rail sector. It's not implemented yet, but of course it's intended to be included to the positioning. The Egnos for rail, once the standardization process is done. We also implemented only the classical ARIME concept that's used for aviation. It's not really fitting to the application. It needs to be modified for road applications or for rail applications. And also ARIME itself alone does not fully protect or fully issues safety. It's one of multiple integrity monitors. In this case, in the navigation engine, but there are other monitors in the baseband or the navigation foreseen to reach full integrity. So ARIME and Egnos are only parts of it. I hope this answers the questions. It's not really fitting together. You're completely right.
Okay. So thanks a lot to you, and thanks a lot for all the questions you've sent to us, and we hope we answered them all right for you. And now it's time for a short coffee break before we continue with the program. And please be back at 11:25. So have a nice coffee break, and we hope to see you again in 20 minutes.
Okay. Hello again. Welcome back from the coffee break. I hope you enjoyed a good coffee or tea or have prepared one for the next part. And I'm looking forward to the next presentation. But first, I would like to remind you, please use the Q&A section during the presentations or during the next Q&A part to ask your questions, and also have a look at the questions that have been posted and vote your most vote questions that are important or interesting to you, so we can rate and answer them accordingly. The next upcoming sequence will help us to understand the Egnos system and the use for Egnos as a safe system for localization in rail. Egnos is the European Geostationary Navigation Overlay Service. And to learn more about it, I give a warm welcome to Pierrick Grandjean from Airbus. Pierrick is the head of navigation, proposals and studies France in Airbus Defence and Space. Pierrick, the stage is yours.
Okay, thank you, Florian. I guess you hear me well, I hope.
Yes, we can hear you.
Okay, all right. I don't know why my camera, my webcam is not okay. It was this morning, so sorry, you cannot see me. Well, okay, thank you again. Well, I guess most of what I would say now, especially in the beginning, is known by most of the attendees, if not all. But it's quite a reminder, in fact, of the basics. And the question was raised about what is Egnos for in rail and how can it be used. So first of all, Galileo and GPS are, as you know, global satellite navigation systems. They provide the positioning services for standard users, namely the open services that enable us to localize wherever on Earth and at any time. But they are not designed for safety of life positioning for critical applications. Such as train signaling in particular is the topic today. For that purpose of safety of life applications, Egnos was developed and designed. And as you said, Florian, Egnos is the European Geostationary Navigation Overlay Service, the European SBAS for satellite-based augmentation system. It provides on one side the corrections on satellite orbits and clocks and ionospheric error maps to improve the accuracy drastically as compared to Galileo GPS. And it provides also integrity bounds and some parameters and alerts that are really dedicated for safety of life applications. and that enable the aviation, the receivers in planes for aviation to compute their protection level and to check the integrity. As of today, Egnos V2 is operational and augments GPS. And in the next years to come, Egnos V3 will become operational in a few years. Just after, the second version of V3, DFMC for dual frequency multi-constellation, will in addition augment also Galileo. And this will also increase the performance and accuracy by using the 2 constellations instead of 1. So what is the current usage of Egnos? Egnos was designed for aviation needs, and it is today a success. In Europe, more than 700 certified approach procedures are using Egnos today in Europe. It has been the 10th anniversary for Egnos safety of flight for aviation, and that's very important now. It's a really common usage for aviation. Now the European Commission, together with the USPA, the Agency for Space Programs, and ESA, the Space Agency, also support other segments to adopt Egnos for safety of flight applications. And rail is one of the most important ones, also for maritime and automotive and US. In fact, what are the railway needs with respect to aviation? As Valentin answered some time before, in fact, the railway needs are higher than for aviation. It may be surprising, but it is. First, the integrity risk or the tolerable hazard rate is in fact 100 times higher than for aviation, 10-9 with respect to 10-7 or 6 per hour. That's one big challenge, and we'll see later on how we can tackle that. And then also what we call the maximum confidence interval size is about 10 meters at low speed, and on speed 2 kilometers per hour, and that's smaller than for aviation. We speak typically of 30 or 40 meters in position, and no safety confidence interval on speed in aviation. So that's more stringent needs for rail. In addition, in fact, the operational environment in which trains are running is more challenging than for aviation, where planes are mainly flying in open sky with a direct connection to satellites. When we are on the ground, and especially on the railways, satellite signals will be masked sometimes by slopes, by the mountains, buildings, and even more inside tunnels, of course. And also, not only masked, but also they can be reflected or diffracted, and anyway disturbed by the environment. And the reflection of signals on buildings is one of the most important source of errors in urban environment or in suburban one. So that's why, as explained by Arnaud before, and Moutou, we decided in fact to develop and to design a multi-sensor fusion-based solution with a tight coupling between GNSS and INS, and this is for improved performance with respect to loose coupling. And in addition to that, we need also detection and exclusion filters to detect and exclude faulty measurements, and also algorithm to compute the safe confidence interval. For this type of solution, we need Egnos, and we need also evolutions of Egnos in top of Egnos DFMC. What are these evolutions that we propose and that we think are important? First, the Egnos service performance must be defined at a pseudo-range level that is different from aviation. So it's a different concept, even if the Egnos system must not be modified for that. but it's a different level of requirements. In the short term, railway should be able to use Egnos v3 DFMC with improved availability and accuracy with respect to Egnos v2, with what we call commitments on performance at pseudo-range level. And in the midterm, by 2030, let's say, a new Egnos Safety for Rail service could be put in place with additional augmentation data that should allow, in fact, to reduce the size of the confidence interval and to reach the most stringent requirements for rail. Also, we need an important evolution on the dissemination to complement, in fact, the geo broadcast by the geostationary satellite by using terrestrial networks provided by rail to improve the access of the Egnos information on board the trains everywhere, and still in a safe way. So that's the end of this short presentation about Egnos usage for rail. We now suggest that we look at a short video illustrating the outcomes of a USPA project where SNCF and Airbus also contributed, that is aimed at the definition of these services for usage of Egnos by rail, DFMC for rail, and the Egnos for rail. So if Arnaud, you can launch the video. I guess we'll see the image, but not the sound, I guess. It's a very short video, less than 1 minute.
The railway operator's objective, including SNCF, is to reach onboard continuous localization for safety operations with the help of game changers such as the European Global Navigation Satellite Systems, GNSS, Egnos, and Galileo. The current Egnos Safety of Life service has been designed for aviation and would require a future complementary service dedicated to terrestrial users to meet the required performances for rail operations. In this context, SNCF and Airbus Defence and Space joined hands to assess the feasibility of such a GNSS-based rail safety service in the frame of the GNSSR mission study funded by the European Commission and supported by USPA.
Normally it's done. Do you hear me?
Yes.
Yes.
Okay.
Yes, Arnaud,
Thank you
that's
very
fine.
much.
We're on time.
And the sound was
Great.
good?
Perfect.
We could see and hear the video. That was
Perfect.
great. So thank you very much, Birg. Next topic will be localization, which uses GNSS, needs and involves the creation of a digital map. And that digital map is needed to map match and localize the train in an absolute position. So how is this digital map specified and how is it defined in CLUG? Let's have a look at the details in the next session with Henning Nitschke. Henning Nitschke is from Deutsche Bahn and the digital map expert, product owner and work package lead in the CLUG project. Welcome, Henning.
Yeah, thank you, Florian, and hello, everyone. Hope you can hear me and see the presentation.
Yes.
Perfect. So, yeah, digital map was already mentioned very often today, and yeah, now it's time to talk about it. And I'm happy to have the opportunity to do so today. Let's start here. I just activate the laser pointer. Okay. So in the project, it was our mission to specify the digital map on the air gap between the trackside digital map management and the digital map onboard system as an initial part of the CLUG localization system. Together with our project partners from SBB, SNCF, Siemens, Airbus, and Naventic, we specified the map content, a map structure, and a map model. as Mutu perfectly answered in the Q&A. Whereas digital maps in the railway context could cover a wide range of use cases, in the CLUG project we focused only on the localization system to enable following system functionalities. So first one, map matching of the 3D position to a linear movement along the current track edge. Then the track selectivity algorithm to determine the current track edge ID as Arnaud presented, and to bound the errors of the inertial sensors using map data. Our specification work in the project followed 5 main design criteria. Our digital map specification describes a machine-readable representation of the railway network. We tried to find a solution which is usable for long-term and universally extendable for other railway-specific use cases beyond the localization. You could think about the capacity and traffic management system as an additional consumer who also needs infrastructure data. The fourth one, the map should be structured as simple as possible. I will show you later in detail when presenting the data model. And last, we use a map structure to avoid redundancies as a common way to reduce systematic errors. Besides the design criteria, we fulfill the corresponding CLUG high-level system requirements with the map specification. I will now show you step by step. First one, the definition of the required content of the map was an important part of our work. We defined a minimum setup of data with our colleagues in the project. So the data contains, the mandatory data contains the topology of the railway network with all the logical connections between nodes and edges, and a representation of the track center line with absolute coordinates. You can see on the right side, a track center line point is located on the same height as the top of the rails and in the middle of the track gauge. In addition, we also defined optional data, which could support the algorithm. Here we talk about the representation of balise groups and the single balises and the position of the single balises inside these groups, and about the representation of the track geometry with information about the curvature, the cans, and the gradients. In the next step, we designed a very lean but clever data model to fulfill the needs of the localization algorithm. We use only 3 object classes with logical connections to describe the physical railway network and its required attributes: track nodes, track edges, and attribute points. That's how we can ensure the data distribution on different layers without redundancies and according to the needs of the localization system. Let me show it to you more in detail. You can see a simple example on the right side. First one, we use track nodes to represent points, system borders, or track ends. Every track node here has a unique identifier and its track node type. So in this case, point, pseudo, or track end, track node. Then second, we use the track edges to represent the physical sections, railway sections between the track nodes. Here, every track edge has a unique identifier as well, through length, and a start and an end track node, just to describe the attributes along the track edge. And last but not least, we also use the attribute points to represent the attributes of tracks, like the track center line and 3D coordinates, or elements of the tracks, like the position of balises, as mentioned before. Every attribute points here has a referenciation, have a reference to its track edge, and an offset to the start track node based on the true length of the track edge. It's important to say that this data model is, of course, extendable and can accommodate future needs easily with adding further object classes, for example, navigability for a traffic management system. Now I will show you how our map structure works. You can see here the visualization of it. The basis is the base layer with the topology model. You see it here on the bottom. It's the classic node edge model with track nodes to represent these 3 points here, and the track edges in between. On the next layer, the track center line layer, you can find the representation of the track center line using attribute points. As already mentioned, in this layer, every attribute point has a reference to the track edge, an offset to the start track node, based on the true length, and of course the values of the attribute points. In this case, it's 3D coordinates. For the CLUG project, we decided to use WGS84 coordinates, longitude, latitude, and altitude. This data here will be used as reference points in the localization algorithm. You can also see that the attributes points have dynamic distances in between, with a minimum of 10 meters for the smallest curve radius of 150 meters, which is allowed in our interoperable railway network. This minimum distance of 10 meters is a result of the error budget and an analysis done by Airbus. In the next layer above, there is the optional data, which could support the algorithm, as mentioned before, to bound errors of the inertial sensors, for example. So let's take the curve radius layer. Attribute points are placed at every location where the value in the track layout changes. You can see it here. The track comes from the left side with a radius of 10,000 meters. And directly at the start of this point here, the radius changes with 706.3 meters, and that's exactly where the attribute point is placed. In this case, of course, with an offset of 0 meters along the track edge, because it's placed directly on the track node. The other optional data follows the same principle. So let's take a look one level more in detail. Here you can see an extract how the data could look like on the air gap. On the air gap, you will receive a list with every values for each single track edge. In this example, it's again the curve radius layer. We have 3 iterations here in this track edge. The first one is again our attribute point directly at the start of the switch with an offset of 0 meter and with a value change to the upcoming curvature. So the curvature is the reciprocal value of the curve radius. We also added the azimut, so the direction angle between north and the upcoming track sections as an additional information. The second iteration is the attribute point after 54.5 meters. Here the value changes to 725 meters, and of course the azimut changes as well. The last iteration after 90.73 meters, here you can see the reason why we decided to display the curvature instead of the curve radius. Here we have a value change to a straight with a curve radius of infinite. Yeah, and we don't want we wanted to avoid the infinite value in our data. So these lists will be provided for every track edge and separated for every layer, for every different information. Let's come to the conclusions and the next steps. Yeah, at the end, I can say that our work for the map specification was a successful joint venture on European level. We designed a digital map specification which ensures interoperability, for example, with improving the existing RCA topology model based on inputs from the project. We also designed specified a future-proven solution with our map specification with following the design principles I mentioned before. But of course, we also know that there's still a lot of work to do. To guarantee a uniform data quality all over Europe, we need to standardize a data management process. This data management process will, of course, include data validation mechanisms. That's what Mutu also mentioned before in the Q&A. Here, we as the infrastructure managers and the railway undertakings have a special responsibility. Also, the data distribution process needs to be defined to ensure that every train always has the current infrastructure data available on board. Yeah, now I just have to say thanks for listening, and I hand over back to our moderator, Florian.
Thank you very much, Henning. I think the digital map was a very interesting topic for many in the audience, and we see a lot of questions. So in this CLUG project, also a performance and safety analysis was conducted, and both providing high performance with a very high safety at the same time is crucial for a CCS localization system in the future. And the performance and safety analysis will be presented by Pierrick Grandjean again from Airbus. Pierrick is the head of navigation proposals and studies in France in Airbus Defence and Space. Pierrick, the floor is yours again. Welcome back.
Okay, yes, I'm still here. I guess
we can hear you.
On the slides. Yes, okay. Okay, so as you said, yes, main topic is about performance, and especially what we call performance for integrity, meaning the confidence interval size, and we'll first start with a few important definitions. And do you have the slides visible on your side? It's not the case on mine.
Yes.
Okay, so we can move to the next slide. Yes. Okay, all right.
Normally, I'm displaying the performance term definitions right now.
Okay, that's fine. So thanks. So we are speaking about here the state parameters that we wish to estimate, and we wish to have a safe confidence interval on each one. Here, these position parameters are the along track distance with respect to the last reference point, the track ID, the velocity, and the acceleration. Here we will focus on the along track position and velocity on this presentation. Here the topic is to be able to anticipate and to predict what could be the performance of the TLOBU using Egnos. Okay, next. Now we have what is the error? The error is the difference between the estimated position and the true position of the train front end. What we speak about accuracy, that is one performance item, is a statistical range of the error, the position error. Usually, we're speaking of 99%, 3 sigma, if the distribution is Gaussian, or 2 sigma. Now, when we speak of integrity, it's a different topic. We are speaking of confidence interval with respect to an integrity risk. An integrity risk is the probability that the error is larger than the bounds of the confidence interval, and so the confidence interval is the width or the place where the true position of the train must be placed with a given probability. So the integrity risk is the probability that it exceeds, and usually it's very low. And typically in the train, it's typically 10 minus 9 for SIL4, 10 minus less for SIL3 and SIL2. And in Egnos for aviation, it's typically 10 minus 6 per hour approximately. And next is the performance that we expect. So the train is safe if the true position is within the confidence interval. Then we have a requirement at the operational level that is the maximum confidence interval for a given operation. And this is the requirement that has been defined in the work package 2, in fact. Meaning that if the confidence interval is lower or smaller than the maximum one, MCI, then the operations are nominal and everything goes as planned. If the CI is larger than the MCI, then we have some operational constraints, meaning that the train may be slowed down, lated, or affect the traffic density. But so the confidence interval itself and the integrity risk is a safety issue, and this is mandatory for the safety of the train, with a very low probability corresponding to the sea level. And the maximum confidence interval is in fact an operational performance, but it's not a safety issue. So here we will assume that the integrity risk is satisfied by definition, by design, and we look at the confidence interval feasible size given the different topics. First, in fact, this field event that is what we call the yes, you can keep the next one, that's fine. This field event, the fact that the position is outside the confidence interval, is a catastrophic event, and this can come from two causes, in fact. The first one is a statistical fact that the error can be larger, and this is what is assumed in the design. And then it can be a faulty case of the system itself, including Egnos and including the TLOBU. And this is a safety analysis. We also conducted a safety analysis in CLUG with first top-down qualitative analysis and then a quantitative analysis from bottom-up, from the design, to demonstrate what is the reachable seal level. It has been based on the definition of 2 phases, depending on the availability of GNSS data, and some assumptions about the data fault detection and exclusion capacity, or their availability, the dependability, in fact, at the seal3 or seal4 level, and also the failure probabilities of the IMU and the Egnos system. Based on these assumptions and the safety analysis, the fault trees, we derived several conclusions. The first one is to be able to avoid the catastrophic events. The failure detection and exclusion algorithms are of high importance, and we also will have to add some redundancy at the level of the sensors typically, and at the quantitative level, with the assumption that we made on the slides before, we assume that at this level, the CLUG design is compatible with the seal3 target. It's already a promising stage. Of course, it can be improved and it should be improved to reach the seal4 target. But already at this stage, it's a very good result, in fact, in CLUG. It will be, of course, continued in the next stage. At the safety level, the solutions ahead are first to rework on the seal level requirements at the TLOBU level, and also to add some redundancies inside the TLOBU also to reach the seal4. When we turn to the estimate of the size of the confidence interval, we have to take into account several things. First, it's the fact that due to the usage of GNSS, the performance of GNSS will not be constant in time and in the user location. It depends on the satellite visibility, the number of satellites in the sky, and their respective position. That is called the DOP, illustrated on the right. It's not the same accuracy depending on the satellite constellation geometry. Then also it depends on the local environment that will mask some satellites and also provoke some field events, local field events that will be detected or not by the data FDE. This is very important to take into account in the capacity to derive a size of the confidence interval. And if we look on the figure above, that is an illustration, of course, it's not real data, but we'll see that depending on the environment and the satellite geometry, the size of the confidence interval will change in time. It will be low in open sky, it will grow up in buildings or urban areas, it will grow up even more in tunnels where GNSS is not available due to the derive of the IMU, and then it will come back if we go back to open sky. The good question is, will we be available to be under the maximum confidence interval corresponding to the ongoing operation? For instance, if we are inside the train station, we'll have a more stringent requirement due to the low speed. Then the global level is also depending on the GNSS and the sensors error models and integrity models after the correction by SBAS. So we need to model the GNSS system errors and the local environment models of the field events. Of course, also the IMU and the track map are subject to errors that have to be modeled. In this analysis, the purpose was to derive the feasible performance without the balises, meaning that if in some places the requirements are not fulfilled, one solution is to add physical balise to reach that performance, or to improve the sensors or the GNSS performance. If we look now at the performance general prediction approach, that is derived, in fact, from the approach that at Airbus we conduct and we developed for aviation. The first thing is that we are looking at a statistical distribution of the capability, because as we have seen, it depends a lot of the geometry and the local environment. So we first made a prediction depending on the several things. First, discretization of the user location and time, and the track direction, because the global accuracy will not be homogeneous in the direction due to the satellite constellation geometry. Then we also simulated, in fact, models of the environment and the FDE by modeling, in fact, the impact on the Kalman filter measurements by GNSS on two levels. First, masking and discarding of satellites by the data exclusion algorithms with different ratio that we tested the sensibility of the performance with ratio depending on the environment, and also some masking models with probabilistic models depending on three types of environment: clear sky, suburban, and urban, where the masking and the fear event probability is higher. Also, we we estimated the sensitivity of the confidence interval size with respect to the residual local errors statistical model from a very low level to below 1 meter and several meters. We expect the standard here to be around 1 meter because this is after the FDE detection. Then we processed, in fact, all these hypotheses for each point, each time, each hypothesis about the masking, the environment, and the FDE computation to predict, in fact, the behavior of the fusion filter model, including also the error models from Egnos, that is a detailed macro model of the Egnos system. And this provides a prediction of the state covariance at the output of the Kalman filter. Then this is translated into a confidence interval thanks to projection on the track map, on the track direction, sorry, and taking into account the safety factor corresponding to the THR. Then this drives, in fact, statistics on potential confidence interval values depending on all these parameters. And we looked at the feasible confidence interval for a 99.9 availability. And here we have a typical distribution of possible confidence interval size in urban environment, and with maximum confidence interval corresponding to the 99.9% availability. The next slide gives an overview of the results for this 99.9 availability reachable confidence interval. Here we show the feasible confidence interval size for position and speed in the three types of environment, and depending on the hypothesis of data FDE exclusion and residual error that corresponds to the values of the CI. What we see is that globally in open sky, whatever the FDE behavior, we should be compliant to the 10 meters requirement. That's very good news with Egnos DFMC. In suburban, it will depend on the environment and the strength or the impact of the environment on the signals, and depending on the exclusion ratio due to the data exclusion algorithms. And in urban environment, mostly the performance of 10 meters cannot be reached, whatever the context, due to the masking mainly. It's approximately the same conclusion for speed. In this means that for reaching this type of requirements in urban and suburban, we need some improvements. One is to place physical balance to improve and to reduce the confidence interval regularly. The other one is to use potential enhanced service from Egnos for rail, that will provide, in fact, additional parameters necessary for the Kalman filter CI computation, but that has to be assumed as an upper bound using the FMC, and that can be provided as dynamic values with this new Egnos for rail service. So the way forward for us in the next project is to complement this CI prediction, including better modeling of the computation algorithm and the data FDE, better modeling also of correlation and biases that are taken into account, and also to account for the GNSS denied areas and for the IMU, I mean the without GNSS, and to take into account this future service that we propose to evaluate the benefit quantitatively on the performance. So that is the last slide. Sorry, this is a backup in case we need it for answering some questions. Thank you for your attention. We'll be pleased to answer questions, of course.
So, thank you very much, Pierrick. Yeah, as you already said, it's now time for our next Q&A session, and I think we have quite a lot of questions. So let's start with you, Pierrick, and have a look at the question you've sent to us. So, Pierrick, which sigma are assumed for the confidence interval numbers shown? It's the first question.
Well, yes, okay. In fact, it's not really a sigma, but I understand the question. The confidence interval requirements shown from our package 2 and the requirements are for an integrity risk of 10-9 per hour. That is for the requirements. In the performance evaluation analysis that we just presented, the values are for the 10-6 per hour, meaning, as we said also, that for reaching 10-9, we need some redundancy and combining several solutions, or to revise the requirement down to 10-6 per hour.
So next question is, will the Airbus solution work if Egnos is not available? Why not try the use GNSS first with balises and IMU?
I may answer. Do you hear me?
Yes.
Yes.
Okay, so the question is the availability about Egnos. We already answered that currently for aviations, main dissemination broadcast for aviation is done by two redundant, in hot redundancy geostationary satellite. For railway, it is not enough. So we also already mentioned that the Egnos dissemination data should be done mainly by the ground. So it should be a purpose of having redundancy on ground, but also redunding by space dissemination. That could be geo, but also future other satellites that are not geo. And if the question is regarding the Egnos availability itself, so the capacity to provide the message, then I would say it's the same question, it's the same answer for GPS and Galileo. All these three constellations needs to be available. So provide capacity and availability on that. Why not trying to use GNSS first with balise and IMU? Why not? But it does not answer clearly the point of the safety, because using GPS and Galileo is already used by a non-safety application by the train. And so using only GPS and Galileo does not offer added value in the safety angles. Here we have only balises in the current system and odometer systems that are safety usable. And in the future system, IMU is a point why not balises? But the added value from GNSS is not so important. If you want to add some things, if someone want to complete Pierrick or
yeah, that's fine. I mean, we need Egnos for integrity, unless RIM, but we choose Egnos, in fact, to base the safety requirements and to improve the accuracy.
Okay, so thanks. So next one is considering the Kalman filtering approach taken in CLUG. How do you account for the effect of biases and time correlation of remaining error distribution after correction?
Well, that's a very good question, and indeed, it's a main topic. We have worked very heavily on this one. This should need, in fact, a long answer that I cannot give here in a short sentence. But yes, the time correlation is taken into account in the Kalman filter first, and in the computation of the confidence interval. Today, this algorithm is at the level of design. It has not been implemented in the experimentation phase for CLUG. We are today in the stage of this detailed design and prototyping. But clearly, yes, this is the main topic. And that's why also the next Egnos for Rail new service is proposed, is to replace, in fact, this time correlation model and biases from static values that must be defined for the FMC, for the use by algorithms, to distribute dynamic values from Egnos to provide a better performance. So yes, this has to be taken into account in both algorithms. And we have solutions, but it's tricky.
Thanks for that. So next question is, what were the reasons and advantages of using Egnos SBAS over RTK? To my knowledge, at least the RTK positioning accuracy is supposed to be much better than that of SBAS.
Well, it's right that RTK provides better accuracy, but to our knowledge, it does not provide safety, just like for other solutions like PPP or high accuracy services. So back again, we need SBAS for ensuring safety on the confidence intervals. And developing a safe RTK, to our knowledge, is not yet foreseen by any RTK service provider.
Okay. So thanks for that. And so now we have a lot of questions for Henning, I think. So let's start with it and see how far we get. So Henning, which reference system has been selected for the coordinates? ITRF, ETRF, or other?
Yes, as I described, all absolute coordinates will be displayed in WGS84, and the WGS84 is based on ITRF, the International Terrestrial Reference Frame.
Okay, and next one also for you, will be the digital map be part of a future TSI? Is the data format already standardized and agreed with the industry?
So to the first part, hopefully yes. I know, or we know, there's a lot of work that needs to be done for it, but yeah, it's targeted. And is the data format already standardized and agreed with the industry? Yeah, that's the next step. Most of you already heard about the RCA digital map cluster, where a lot of standardization activities has been done yet, and the next step is within the system pillar of the RGU, the alignment with the industry of all these results, and yeah, that's next steps.
Okay, and is the data model aligned with the RCA digital map object catalog specification?
Yes, as it is based on the RCA domain knowledge topology, as I described, it is also aligned with the object catalog. And luckily, I'm also a member of the RCA digital map cluster, so I could directly take care of it.
Okay. So, and why do you use WGS 84, sorry, instead of, for example, ETRS 89, correction of continental plate shift for the map?
Yeah, I really like this question. So WGS 84 was a project decision done by the whole consortium. But of course, I totally agree from a map perspective, ETRS 89 would be the much better solution. The advantage is clear. The coordinates will not change due to continental drifts. But the solution with ETRS 89 is envisioned by the RCA Digital Map Cluster.
Okay, thanks. And how do you describe transition curve? Do you consider a change of curvature is done at once?
Yeah, as we know in a transition curve, the radius changes permanently, and therefore the curve radius or the curvature points, the attribute points in the transition curve, could be evenly distributed over the length of the transition curve with a maximum distance of these 10 meters mentioned in my presentation, based on the 150 meter minimum radius. Yeah. That could be one solution. Of course, there could be others.
Okay, so thanks. And what about the reference to any geodetic coordinate system? How can existing track data maps can be converted?
Yeah, I think there are a lot of transformation parameters defined from WGS 84 to ETRS and the other way around. And also talking about the DBREF, which is used within Deutsche Bahn, there are fixed parameters for the transformation from DBREF to ETRS 89. Of course, we need to take care with the transformation from WGS 84 coordinates with the epochs of the measurements. And but then I think with taking care of it, the parameters are clear to make the transformation.
Okay. And did you assess the feasibility of providing a SOL service through 5G telecommunications network?
Not in the CLUG project. Of course, we know it will be an air gap interface. Based on future mobile communication systems, FRMCS. But yeah, no, we did not assess any feasibilities, no.
And is the digital map format compatible with a Rail ML or Rail Topo model?
Yeah, as long as it is our CLUG model is based on the RCA topology model, as mentioned, it is the conformity to the Rail. The new name is the Rail system model, is guaranteed. We had some studies of it within Deutsche Bahn to guarantee a transformation from one model to the others, and yeah, that this will work definitely.
Okay. And how do you describe transition curves? Do you consider a change of curvature is done at once?
I think this question.
I think it's double. So, so next one is the digital map trackside system going to basis for ATO and interlocking track information needs as well? And is it going to be under SILK requirements?
So it's planned that the digital map will be the basis for ATO and also for interlocking. For example, I think in the next question, it's already mentioned in the digital node Stuttgart. We are we from Deutsche Bahn exactly developing a digital map to provide segment profiles to ATO trackside. And in the ERGU innovation pillar activities, there will be the so-called moving block demonstrator, where the APS will be demonstrated, and also therefore a digital map is part of it, or will be part of it. Yeah, exactly. And then we have exactly these the requirements to be considered for the map. Yeah.
Okay. So, and how much manual programming effort will be needed for creating and maintaining such a digital map? Is this somehow quantifiable, for example, for the digital node Stuttgart?
Yeah, very good question. I'm responsible for the development of the digital map in the digital node Stuttgart. And last year we did a proof of concept to analyze the feasibility of the transformation of Plan Pro and Spurplan data. These are common use data formats within Deutsche Bahn for planning ETCS and so on, and also for the scheduling of train operation. And yeah, we showed that it works. It will work automatically, and I think the manual effort will be as small as possible. We will have the problem that we cannot guarantee automatic interfaces, so there will be manual interfaces, and so there needs to be manual effort. But hopefully it will be as small as possible.
Okay. So thanks, Henning. I guess now we can come to the questions for Pierrick again. So Pierrick, did you perform the safety quantitative demonstration by using real GNSS data or simulations?
Well, these are in fact predictions, so it's not real data. Yes, it's simulations of the constellation and Egnos system. Yes, this is prediction. It has to be confirmed. It has to be confirmed by experimental testing, of course. But experimental testing will never cover all the cases of all time, everywhere, and all the types of environment. So that's why for assessing the performance of the solution, we have also to perform simulations to be confirmed by experimentations. Yes.
Okay. And did the train station mentioned in the confidence interval graph with an open or closed roof?
Well, interesting question. Yes, well, this was really just an illustration to show that the CI value will not be constant, and that will depend on the environment. I would say that, of course, yes, the performance will not be the same in an open station or even an open sky station, let's say, in the landscape, or in a station with roof that is more like a tunnel, in fact. So this was an illustration. We can expect, yes, some stations to behave like tunnels.
So next question.
So I cannot tell.
Yeah. Okay.
Drawing. It will. Okay. Next one.
Okay. Next one is tachometer speed was classified with no safety level. How can this be used to replace the GNSS signal in mask areas to fulfill THR values?
Maybe I could answer. So Arno speaking. Yes. In fact, I guess the question is guessing that it's loose coupling parts. There is no, let's say, replacement between the sensor each other when one is not available or the rate of providing the data is not the same, and etc. Here we are in a high tightening coupling concept. So there is no things to say that it replaces the GNSS signal, but it completes the data. And so the speed sensor is used even not classified as safety levels, because after it, there could be FDE, data fault detection and exclusion, providing a certain filtering safety aspect. And then all the data, so coming from the IMU and from the TACO, even if we don't have the GNSS signal, are tightly coupling in the fusion algorithm. So let's say that when we have RF masking, the main sensor to lead is the IMU, but speed tachometer nevertheless contribute at least to reduce the bias from the INS. And I guess you missed one question, Jasmine. Let's go further. At 11:55.
Telecom network, yes, you can answer.
Yes.
Arno, I guess.
Did you assess the feasibility of providing a safety of life service through the 5G telecommunication networks? There is a big topics here on how to disseminate the Egnos message from the ground, from the Egnos centers, let's say, up to the train. And we already answered that it should be done by the ground network. Inside this, it is assumed to be next coming safe network for rail, that its name is FRMCS. I don't remember the acronym of FRMCS, but it is 5G technology, but it is not a public network. And indeed, this FRMCS network that is expected for the rail has to be safe enough to ensure the C3, C4 data that is inside. And it's not only for Egnos, but it is for all the data to be safely shared between the train and the infrastructure. And also, as we were saying, we can this kind of network could be redundant by signal in space dissemination until it is ensured to be safe, like it is currently with the geo broadcast for aviation.
Okay, so thanks for skipping in, and I can help you out with FRMCS. So FRMCS is the Future Railway Mobile Communication System. So that's the abbreviation. So so you helped me and I helped you. So okay, so maybe we can come to the next one. IMUs are relative sensitive devices in terms of performance with varying temperature and regarding excesses of vibration and jerk. Vibration, for example, wheels, flats on the track, jerk, emergency braking. Has performance in these situations been tested?
I would, yes, let's go, Pierrick, but maybe Bernard should be more.
Yes, this is more a question about experimentation. It's right that the performance of IMUs are not also constant on time. And this is more a question about experimentation. So if Bernard is online, maybe he can answer, or we can push these questions to this afternoon, as you like.
Can you hear me?
Yes,
Bernard. We hear you.
So we will touch that subject in the presentations after lunch. We have tested some extreme cases, some provoked, some just by collecting enough data to pick them. So we will look at a few of these things later on.
Okay, so thanks, Bernard. And guess the last question for Pierrick is why only SIL 3? It's not enough for railways. What is the next step to reach SIL 4?
Well, we presented the two ways that things can be tackled in the next stage, the next projects. On one side, we think that we could also revisit the global sea level allocated to TLBU, considering the global system level and maybe some barriers that could be set above the TLBU, or we have also solutions to be, in our drawers to introduce redundancy inside the TLBU to reach that level, typically between one very high safe level TLBU part combined with a lower level to reach the SIL 4 level. So one very safe TLBU part and a lower level combined independently.
I could add that
but this is subject of R&D.
Yes, I could add that in this CLUG stage, so at proof of concept, SIL 3 is already well assessed to be reachable. SIL 4 is also able to be targeted, but it's still OPEX and CAPEX question also between to ensure that the final requirement should be SIL 4 for every parameter that has been requested, and between the technology to be applied on it, if it's SIL 3 is not sufficient, to go up to the SIL 4. So these gaps should be addressed on both sides, as it was mentioned, top down and bottom up, to converge at the end at the real need, or the exact need.
Okay. So I guess we have finished all the questions now, and yeah, thanks for all your questions. This is the end of the CLUG webinar's first part, and it's now time for our well-deserved lunch break, I guess. So we will have the lunch break until 1:30, and so you can be back in 1 hour to continue the journey with us in the CLUG project. And yeah, just enjoy your lunch, and thanks a lot for your attention.
Hello, welcome back. I hope you are all well energized and rested by the break, and you're all ready to learn more about the CLUG project now in the afternoon. Let's start. I'm Florian, and together with Jasmin, I'm moderating the afternoon session today. In the next upcoming sequence, we will focus on another fundamental part of this project, the demonstration and data collection. And as you know or learned today already, the localization system is using a multi-sensor approach and sensor fusion with complex algorithms which calculates the terrain positioning. And those algorithms needs to be developed and tested with data. How to collect and process the data needed, and that both quality and quantity of data is very important, is what we are going to see with Bernhard Stamm and Paul Fritsche next. I'm very happy to welcome Bernhard Stamm from Siemens Mobility. Bernhard is the testing and evaluation lead and a senior key expert from Siemens Mobility. And Paul Fritsche from Deutsche Bahn. Paul is the localization expert at DB here. Welcome, Bernhard. You're live.
Thanks, Florian. Can you hear me?
Yes, thank you.
Okay, thank you. So, yes, we will have two presentations now. The first one is on the actual data collection and data processing. And the second one will then be on the data analysis and the performance data. So the main purpose of Work Package 4 was to actually evaluate the performance of the positioning solutions developed as part of the CLUG project. And as we've seen earlier, there were two separate solutions, one developed by Naventic and one developed by Airbus. And the aim was to test them as if they would be installed on board a train, giving us the true performance in the true environment.
Bernhard, we can see your slides, but don't see your video. Do you want to turn it on, or you prefer the slides only?
Video. Where do I turn it on?
Next to where you share the screen on the camera.
Well, then let's stay with the slides.
Yes, okay.
Okay. So the performance of these algorithms or these solutions is mostly impacted by the environment, by the impact on the sensors produced by the environment, but also on the actual train driving, how you're operating the trains, on operational behaviors, as well as on the trains themselves. We've heard earlier about the question about flat spots on wheels. Yes, any such train-related effects impact the performance of the solutions. These impacts cannot be simulated with artificial test cases, so we saw the need to use real field data for the testing, but then do the testing offline, as the solutions currently only consist of algorithms. They are not built into hardware that we could install on trains. So to do that, we had to develop various tools and processes, starting with a sensor collection, sensor data collection. And then we had to, of course, convert that data into harmonized formats. We had to process it with the algorithms. We had to generate a true reference with reference speed, reference data against which we actually evaluate the performance. And then we also, of course, had to do the actual analysis and visualize the data. That resulted in a fairly complex process, which can be seen on this slide. Let me just, can you see my mouse?
Yes.
Yeah, okay. So
yes, we see it.
Okay, thank you. So the The process can be split into 4 different stages. The first one is the yellow one, where we actually collect static input. So we collect algorithms from work package 3. We collected requirements on sensors. We collected operational scenarios and mission requirements and produced a test plan. So this was done once at the start of the project. And then we went into the second phase, which is the blue phase, where we actually collect data on board trains, where we record the data, where we process this, where we convert all the data into harmonized formats, because the different trains use different recording equipment, also different sensors. In that phase, we also collected infrastructure data, map data, Egnos data from the EDAS service, even weather data. And in that phase, we also generated the true position, true speed, etc., which we call the ground truth. This was a continuously running process, so we collected data for about 1.5 years and just built up a stock of raw data, which is then processed. Next phase is the green one. That's the actual sensor fusion, where we, in 2 parallel streams with a platform from Naventic and one from Siemens for the Airbus algorithm, actually run the raw data through the algorithms, produced PVT plus outputs, so speed, position, attitude, etc. And in that step, we also compared that data with the ground truth, and we also produced a lot of plots for visualization. That is typically done once per trip, unless we get updated algorithms, then we can rerun that step and see how the difference, how they perform differently. The last step is the red one, the interpretation of the results, where we actually jointly with different partners look at the data, try to interpret it, try to identify data elements which impact performance, and try to draw conclusions to improve the algorithms. So here now in this presentation, we cover that part, and in the next presentation, we then look at the actual plots and analysis results. This is basically the same as seen from a data flow point of view. So on the left side, we collect all the raw data in different formats, depending on the train, on the equipment used. This is then processed individually by the 3 partners operating the 3 trains, generating a set of harmonized raw data, which is actually a public deliverable. So this is what we will deliver as deliverable D4.2, so that also other external organizations can try to analyze that data. This is then run through the fusion, generating PVT plus data, and then through the data analysis tools where we generate the results. Next, we of course had to have test trains to collect data. And on these test trains, we of course also had to install a lot of equipment, sensors, antennas, etc. We decided to try to have 3 trains, one each in Switzerland, in Germany, and in France, in order to get a broader coverage of different environments. You can see, for example, the German train can run on high speeds, while the Swiss train is a local train which does not run at speeds above 140 kilometers an hour. So to get a broad coverage, we had 3 test trains. Next thing was that we had to make sure that with these trains we collect sufficient amounts of data. And the problem is that many occurrences which impact performance don't happen on a schedule. They happen randomly. They cannot really be controlled. If you want to catch certain weather conditions, for example, then you just have to continuously record data, hoping that you catch those days where the events of interest do happen. Let's have a look at the 3 test trains. So the first test train was a domino train. It's the one in front of the 2. from SBB. That's a train operating in commercial service, which makes testing a bit more critical. It has been built in the late 90s, so it's not the newest, smoothest running train, which is good for testing because it has less than optimum conditions for certain sensors. Let's call it like that. The train still has a baggage compartment, which is not used anymore operationally, so it provides ample space for installing equipment, as can be seen on the picture on the right. That train has already been used for similar work in the STARS project, and that was also one of the reasons why we picked it, because like that we did not have to recertify the entire installation, and we thought we could start collecting data very quickly. Still, also on that train, we had to do a number of changes for the CLUG project. We installed, for example, a second multiband antenna so that we can do measurements with dual antennas. We installed, as can be seen on the upper right, a Corail sensor. That's a sensor that measures speed looking at the railhead with detecting the movement of the rail. It is independent of slip and slide and therefore provides a much more accurate speed than the tachos. We also installed a high resolution tacho on one of the axles to see whether the resolution provided by the tacho, the number of pulses per rotation, could have a significant impact. And we updated our two radars installed on that train. We have two test radars with firmware which was specifically suited for testing. Just when we wanted to install equipment, COVID started, so we had some delays there, but still, thanks to the flexibility and support from SBB, we managed to install all the equipment between August and October 2020 so that we could start data collection with only a few months delay in November 2020. The next train will be presented by Paul.
Yeah, hello everyone. My name is Paul Fritsche. Thank you for coming back after the break. So I have a short part in this presentation. I just wanted to show you our test train at Deutsche Bahn. It is the Advanced Train Lab. The Advanced Train is the purpose that it's accelerating the innovation coming from industry and science to bring it into the real. And we already have many projects and cooperation running in different fields of technologies, as for example in sensor technologies, as for example in CLUG, connectivity, green vehicles, ETCS, and so on. And since we already have some experience, we already established a kind of process. So we starting, usually someone get in contact with us with an idea and a need, and then it's already almost a process already because we have some experience to bring it to the day where we really have test runs in the end. And on the next slide, I can give you a short view to how it looks then behind the scenes. Are some photos from the construction phase. Similar to the previous train, we also installed multi-band antennas as in the picture 7. We also have a Doppler radar and the 5, as well a Corail sensor and 4 and 6, also a tacho. Since we want to share same type of data in the project, we also need similar or same sensor technologies. And in 8, on figure 8, you can see how it looks in the inside. There we have 2 racks and a recording system. And inside we have all our GPS receivers, our IMU sensors, and it's even fireproofed, our rack, because a problem usually is if you bring non-rail certified hardware on the train, that the not existing certification is usually a problem. But this we can cover, for example, in our setup. Okay, thank you for the time. This was everything from my regarding the advanced train lab.
Thanks, Paul. Then we had a third train, which was a former passenger baggage coach from SNCF called Martin, which has been converted into a test lab, also outside the frame of the CLUG project. Martin can be pulled by any kind of locomotive, so it can be used on any railway line in France, whether electrified or not, up to certain speeds, I think 230 kilometers an hour. Also on Martin, a number of additional sensors had to be installed and antennas for the CLUG project, so a very similar situation as with the two other trains. And again, also in Martin, a lot of pre-existing installation could be reused, speeding up the process. In France, measurements were performed only on dedicated test runs, specifically scheduled for the CLUG project. In Germany, that was also done, but there was also the chance to do measurements on test runs scheduled for other projects, as the ATL is used for a number of projects in parallel. And in Switzerland, most data has been collected in commercial operation. But we also had some dedicated test campaigns, I think 5 all in all, each lasting 2 or 3 days, where we went on to less traveled routes and where we did test cases which normally don't happen in commercial operation. A 3-minute video that was prepared by SNCF on test runs we did between Geneva and Annemasse. It's a line across the border from Switzerland to France. This line is specifically interesting because it has a 10-kilometer section which is underground. And that underground section has many curves, many changes in gradients, multiple stations. So that's not what you normally see in typical tunnels. These tests were performed with a domino train, which we had to get through a special certification process as it operated for a few hundred meters onto the French network. So let's have a look at the video. Can you hear the sound?
No, we can't hear.
Unfortunately not, but there's subtitles.
Sorry?
No sound, no.
Okay, then let's try to...
Bernard, when you share, just add click on the computer sounds also. You can try to do it again.
How do I do that?
Can you stop sharing? And then
Okay.
when starting to share again, there should be a slider to include the computer audio.
Okay, let's try to do that.
This is on the window for sharing. So just before sharing, you have an option to add the sound.
Perfect.
We do some test runs to collect data from multiple sensors for a research project called CLUG, which we do in cooperation with SBB, SNCF, DB, and some other partners.
CLUG's main certified localization unit with GNSS. In the frame of CLUG, all the railway companies try to have the same sensors on their train. We will say that the grade of the sensors are changing from a train to another, so we can share all the data sets we are gathering and collecting on the train. After that, we can use this data on the sensor fusion algorithm we developed in the CLUG project.
Actually, we tried to get more precise information on where the trains are, using satellite positioning combined with other sensors, because GNSS or satellite positioning does not work in certain areas.
Today, SNCF is trying to collect data on the Domino train from Geneva to Annemasse. This line is quite interesting because we have some tunnels, some gradient variations. It's really important to see how the GNSS receiver behaves. So that's why we are trying to investigate some areas with half open part of the tunnels and going out and going in.
Typical elements we see which disturb sensors are buildings, big metallic structures, power lines, tunnels of course, and they impact different sensors in different ways. So we have a number of sensors to give us speed. We have tachos on the wheels, we have radars and some optical sensors. And then we have satellite receivers which give us position. And we are also using accelerometers and gyros to get the movement of the vehicle. The test system is controlled by a standard 19-inch computer which is installed in here, to which I have access via remote access. Then we have down here a data recorder from National Instruments where all the sensor data is fed into and recorded in a time synchronized way down to a few microseconds. On top here we have a number of GNSS receivers from low range to mid range, and underneath, which you can't see, we have a sturdy aluminum plate onto which all the inertial sensors are mounted.
Regarding the circulation authorization, so it has been a bit complicated as this Domino train has never been allowed on the French railroads. So we had to complete an entire study with AEF, which is our test agency, and to submit it to the right authorities. We had to evaluate the safety systems which are on the train and to ensure that we are sharing the same standards. We almost had 20 documents to review. Most of them were in German at first, so they had to translate it in both English and French. The main difficulty in this study was probably to find all the different equivalences between the French and the Swiss standards. So I think we can highlight how beneficial it can be to have a unified signaling system like ERTMS.
Collaboration with our French colleague has been great fun, sometimes a bit challenging, but in the end with good results.
So this was the video. My comment at the end was mostly related to the certification process, which was really complicated to do these test runs. So with these multiple trains, we could collect a lot of data in different environments on many lines. With the Domino, we were focusing more on lower cost sensors, which we think is closer to what we will use in a real product solution. Whereas with Martin and ATL, we were using more higher grade sensors, but we all have also sensors installed of the other grades, and we can in the future try to compare the performance using sensors of different qualities. We collected quite a lot of data. This is just some statistics on what we've collected. All these hours and kilometers are excluding IQ data. IQ data is a raw data from the GNSS band, has only been collected on a limited number of test runs because of the volume this data generates. We then developed a process how to analyze the data, which can be shown here in this circle. So it starts by inserting raw data and the algorithm. We then go through the actual sensor fusion producing PVT+, followed again fully automatic by the analysis where we compare speed, position, and other data with the reference data and generate around 40 different plots, which can then be used for data analysis. This is then followed by data analysis and interpretation, which is largely a manual task where we look at the data, discuss between the partners which data effects do we see, how do they impact the performance, and how could the algorithms be improved to generate a better performance output data. This then goes into the actual development, and then we could repeat that cycle. The main advantage of that process is that we can actually repeat tests with upgraded algorithms again and again, always using exactly the same input data. So the results we are producing get very comparable. If we would actually test on board a train, we couldn't do that because first of all, it's very time consuming to redo tests on trains. And secondly, you never get the same conditions. So it's very difficult to compare data. But with this process, we could just rerun exactly the same runs in bigger numbers again and again with different algorithms, and then see how the performance in the process of algorithm or solution development improves. And this is also one of the key assets of this whole process. Ground truth, just a few words. Of course, we need to know the actual true position and true speed of the train in order to compare the output of our algorithm with the true data. Producing that reference has been done differently in the different countries. In France and Germany, high-end GNSS supported IMUs have been used, combined with post-processing of the data. That method works very well, but it requires a certain coverage of GNSS. So it is not suitable in any location. In Switzerland, we used a different approach because we do have many areas where GNSS coverage is difficult or limited. So we produced our ground truth with a process based on the actual track map we receive. That's what you see on the left. It's the input data from SBB. We then convert that into a proper node and spoke model. We also convert it to WGS84 because the input data is based on Swissgrid references. On that map, we also see the balises. So when we do test runs, we record the balises together with the raw data. From the balises, we can determine the path the train has actually taken, and then use our high-quality odometry sensors to produce intermediate position along the spine of the track map. So like that, we can produce a ground truth which is independent of GNSS and of even IMUs. On the right side here, you see the effects of the environment on, for example, a mu-blocks receiver. So here we get a very nice proper ground truth, which we can then compare with the output data of our fusion algorithm. It's worked so well so that we can also use it completely underground, like in the line to UNMAS. Even there, the ground truth can be produced with consistent high quality. We actually even did some runs through the 57-kilometer long Gotthard-based tunnel, where again we could produce precise ground truth with that method. There's two public deliverables from this first part of this task. One is raw data, as I've already mentioned. So we will publish raw data from a number of representative trips, including data and ground truth data, so that it can be used by third parties to do some investigations on their own. Can you still hear me?
Yes.
Yes.
I just dropped out, kind of. So let's continue. So the other is the actual ground truth. Again, we deliver ground truth data with its raw data so that this data can be used by third parties for their own investigations. That's the first part of my presentation.
Okay, thank you very much, Bernhard and Paul, for this great insight into the sensor setups, the test trains, and also the very nice video. And I would like to invite everyone to download and read the public deliverables, which you can find on the CLUG website about this, and also use the opportunity to ask questions for the next Q&A sessions here later. Once the data has been collected and processed, of course, it also needs to be analyzed and interpreted. And in the upcoming presentation, Bernhard will stay with us and share the details of the tools used for this data analysis and the actual data outcome, and performance analysis. Please welcome again Bernhard Stamm from Siemens Mobility. He who is a senior key expert in localization and the testing evaluation leader. Bernhard, go on.
Okay, let's try to share it again. Okay, so this is the second part. This is now the actual how we analyze the data and some results from our data processing, which we've done so far.
We cannot see the presentation yet, Bernhard. Can you try to share it again?
Strange, because it shows a red frame. Yeah, let's cancel it.
No, it works.
Now it works. Okay. So I have to start with some limitations just to avoid many questions. These limitations were known from the start, so it's not that we did not perform certain work, but we had to restrict the scope of the data analysis, and that is just what is shown here. So first of all, we've only analyzed a subset of the data. We haven't analyzed 100,000 kilometers of data, but only a subset of those trips that we considered of significant interest. The limitations we have defined from the start is we are only using GNSS data from Galileo and GPS plus Egnos V2. We currently only use level 1, L1 and E1 frequencies, so we don't yet have algorithms supporting dual frequencies. The Airbus algorithm does use Egnos, but it uses the Egnos we've downloaded from the EDAS service, so we are already simulating the Egnos for Rail service from Danielle that we hopefully get at one point, and the Naventic algorithm currently doesn't use EDAS Egnos data, neither from EDAS nor from space. The algorithm outputs are performed with map matching, but on the basis that we know the track we are running on. So we do not yet have track selection algorithms. We provide a map to the algorithm which only includes the track train is actually run on. And also the integrity filters are currently not yet part of the algorithm, so we do not yet produce safe confidence intervals. We do produce certain error estimates, and we compare certain data against external requirements, but the safe confidence intervals are not yet implemented. So this is again the process, and now we are up here. So we have produced PBT plus data from our test systems. We have produced a lot of plots, and now we start looking at the data. Data has been analyzed in two different methods. The first one is a statistical analysis, in which we analyze larger sets of data from multiple trips, and where we demonstrate achieved performance, availability, coverage, etc. of our solutions. We can in the future do that, for example, for different seasons, different weather conditions, but this is basically all statistics. This will be used in the future certification process to demonstrate performance, but statistics can also be used for other purposes, for example, for the business case, because we can identify with our statistics where does our solution perform and where would we potentially still have to use balises, just as an example. The second way of analyzing data is a detailed analysis, where we actually look at the detailed outputs, both performance outputs comparing the true speed, the true position with the reference data, but also raw data, like on this plot shown here. This is mostly done to analyze the behavior of the algorithms in detail, to identify root causes which impact fusion performance, and then to derive inputs into the development of the algorithms to improve them, to improve the overall solution. This will but also be used in the future certification because we need to demonstrate the safety of the solution also in extreme situations. We initially thought of using commercial tools, but then we realized that commercial tools are either tied to specific products or they have a limited analysis possibility. So instead, we proposed to use a version of a tool called Runalyzer, which is a MATLAB-based tool developed inside Siemens for data analysis of various kinds. We improved that tool and made a special CLUG version so that we could use all input data from all kind of sensors we're using. We also included the functionality to compare true speed with reference and true position with reference. And we included visualizations of about 40 different plots after discussing what is needed with our partners. With this tool, we could analyze data from all 3 test trains because all the input data is harmonized to the same formats. So regardless of which train the data is from, we can use exactly the same tool and methods for analysis. In order to allow the partners to freely use that tool, we've produced a P-code version and distributed it so all the partners can use the tool themselves, and they can also use this beyond the end of the project to continue working on the data we've produced. Statistics were done by SBB using their Apache Hadoop-based big data platform. This platform can include any kind of data, which then can be merged, which is harmonized to the same frequencies and then visualized in different ways. Here we had to put some limits on the actual analysis, so we have some outliers in the data. For example, where we transition from one data file to the next, we sometimes have spikes, and we had to exclude them to get more interpretable results. Now a few examples. First of all, statistics on a number of satellites visible. That's one of the first things that always is being looked at. So here we see, for example, a comparison of how many GPS satellites do we see, how many Galileo satellites do we see, and what the combined number is. And we nicely see that we see between 4 and 8 Galileo and 6 and 12 GPS satellites, typically, which is also the in line with the number of active satellites of the 2 constellations. This statistic is based on around 30 trips on different lines in that specific area. We also produce statistics with mean figures, standard deviations, etc., as required by the partners who develop the solutions. This is another plot where we see the speed and horizontal position errors, again, as statistics over around 30 trips in the area shown on the map. And here we see the distribution of the errors in relation to the number of position or speed outputs. This is an example where we have a trip analyzed only a single trip with statistics, and where we have collected IQ data. So here we can compare solution A from Airbus and solution B from Naventic with their performance. Here on the lower left plot, again the horizontal position error. We see some differences between the 2 plots, so we can from that derive conclusions on how to improve the algorithms or the solutions. This is a similar analysis, again comparing the 2 solutions. Here it's related to the speed error compared to the true speed. Here we see that the performance in the plot on the lower left looks nearly identical, whereas if we look at the actual lower right plot, we see that there is still a difference in behavior. The solution A has in average smaller errors but it also has some error, some noise at very low speeds, whereas the solution B has some outliers, but lower noise especially at lower speeds, like on this section here, where we run with only around 15 kilometers an hour for a longer distance through a narrow gorge. So again, we can nicely compare the different solutions and analyze the performance. Here are some examples from other trips that we did. One open sky, one cities and tunnels, and one where we did some test cases. On the map, you see the ground truth, and the red dots are all the balises we've read. So you can see there's quite a lot of balises on the Swiss network, which helps us to produce an accurate ground truth. This was a scheduled trip. No, it was a test trip, but it was on a schedule representing a normal train run. So we didn't do any kind of extreme testing. We just run normally along the line. And this is now the plot of interest. On the upper curve, we see the actual speed the train has run. On the right side, we see a longer tunnel where we've run through. The plot in the middle shows the speed error in reference with a thin line to what is currently specified as requirement by UNISIG in the ERTMS specification. So we see we get a pretty accurate speed information just with our GNSS IMU TACO-based algorithm. The speed is typically below 1 kilometer an hour, which is pretty accurate compared to what most ETCS onboard units do achieve. This is even the case in the long tunnel. Here we did some sharp accelerating and braking, but that had no impact on the speed error. The lower plot is the position error, which again remains within plus minus 5 meters on most of the trip. We do have some slight deviations from that, but that's nothing that couldn't be improved. So overall, pretty impressive results for a positioning solution, which does not use absolute references, which only uses the 3 sensors mentioned before. Even in the tunnel, our position error remained very low. This is the line that we've had a look at in the video. So that's the 10-kilometer underground line with many curves, gradient changes, and no GNSS coverage. Here again, we have results of similar quality. We do have here one location where the speed output exceeds the currently specified envelope by UNISIG. The position remains again within plus minus 5 meters over the entire trip. Looking at this specific case in detail, this is now one of the detailed analyses. We can see what has happened here. We had significant slip on both axles and not the usual slip where we have sharp speed changes, but we had a continuous slip of several kilometers an hour over a longer duration, which then led to the algorithm deviating from the true speed. This is again one of the things that we can then use to include the algorithms. This is another line from Biel to Le Verrières. Here we did some testing, provoking extreme slip and slide and doing emergency brakes. Again here, the similar plot, the same plots, speed error, position error. Here we see that the tool actually highlights areas where the error exceeds predefined limits, which is here where we did an emergency brake and then followed by sharp acceleration. Here the speed again deviated about 3-4 kilometers an hour from the true speed, but only for very short time periods, and then it immediately went back into the expected band of ±1 or 2 kilometers an hour. Again, also here position deviated a bit more. If we look at that in detail, so that's a zoom of the same situation. This is where we triggered an emergency brake just inside the tunnel, a short tunnel. We then went out of the tunnel, drove into the next tunnel, came to standstill, then accelerated at full maximum power. Here we got out of the tunnel. It was raining slightly outside, so the rails were slippery, so we had a sharp change in acceleration, even though we did not change the applied power. So this is a bit of an extreme case that you can only do on dedicated test runs. And here we see that the speed has certain deviations outside the limit and the position as well. But this is, again, early testing with early versions of the algorithm, which we are now working on to improve and to cover these cases. All in all, now this is another plot just to show you the raw data. So we can, in our plots, also look at the raw data from all the sensors. Here we see the significant slip events on the axles, on the tachos. Here we see the accelerometers and gyros. We see extreme vibration here where we had slip. You even see that on the gyros. So the whole train body was moving, was shaking. And at the bottom, you see the satellites, the number of satellites received and used by the algorithm. Conclusions we can draw so far. We are only at the start of the data analysis, but we see that both streams show very promising results for both speed and along track position accuracy. If we compare that with what we achieved today in ETCS, that's quite impressive and significantly better what we can produce. This is even valid for challenging environments, like the two cases I've shown between Biel and Leveria actually, and also between Geneva and Annemasse. We see that map matching is really the key for everything. That plays a significant role. Our analysis has helped to improve the algorithms already, so we did a number of improvement cycles, but this was then could not be continued because the tight schedule of the project, but we will continue improving the algorithms and pushing them further. We see that the wheel tachos, which is probably the worst speed sensor you can use because it's highly impacted by slip and slide, has a significant impact. So we will analyze fault detection and exclusion algorithms to improve the situation with the tachos. We've had a number of learnings. One is the track map. The track map needs to be up to date and needs to be accurate. The accuracy is usually not the problem with the SBB map because they are surveyor quality maps. But currently these maps are used for surveying work, for construction work. So when a construction has taken place, it might take a month or two till the map is updated. And then sometimes we had instances where we used map which was not updated, which then leads to errors in the analysis, which are not really errors, but caused by the not up-to-date maps. So having up-to-date maps is going to be an issue, and that really needs to be looked at, how to do that, how to bring them on the trains on a daily basis. Next steps, of course, we will have some plans for how to continue. First of all, we want to extend the solutions to dual frequency on GPS and Galileo. We then plan to use Egnos v3 dual frequency data as soon as it becomes available. We still see some improvements possible in the ground truth, mostly for also analyzing attitude and heading data, which we've started. We would like to analyze or compare the performance impact of different quality sensors, which we haven't done yet. But we have on all the trains, for example, high and low grade GNSS receivers, high and low grade IMUs, and we can rerun the data using a different algorithm, a different IMU or a different GNSS receiver, and then see how the performance changes with different quality of sensors. And of course, in addition, we need additional functionality, which should be part of a follow-up project. One is to create track selectivity, not only a long track position. One is also how to do track selectivity across points. And third of all, we want to look into generating an initial position at startup, even in challenging conditions. That's it from my side. Now I think we can go to the Q&A.
Yes, so thank you very much, Bernhard and Paul. So now, as you already mentioned, it is time for our next Q&A session. So let's have a look at the question you sent to us. So I think the first one is a question for Bernhard. What is the target continuity requirements? What is the considered operation duration?
Could you repeat the question?
What is the target continuity requirements and what is the considered operation duration?
What is meant with operation duration?
How long will it last, I think?
Well, the positioning solution should work all the time. If that is meant regarding how long should it last without GNSS coverage, like in tunnels, this is one of the areas where we are trying to analyze how far can we go. We do have some defined requirements in our input documents, but we haven't yet analyzed how far can we run in situations without GNSS till the errors become too big. But the data from the line to UNMAS shows that we can do that over quite some distance and some time with still very good performance.
Okay, thanks, Bernhard. So next question is for Paul. Paul, it wasn't clear from your slides. So what sensors were installed on the German train, on the ATL?
As in all trains.
Oh, Paul, I can't hear you very well.
Hello, can you hear me? Hello?
Yes, but not very good. Yeah, now it's better.
Okay, so as in all trains, we have, for example, those three odometry technologies like the Tahoe, the wheel encoder, the Doppler radar, as well as the optical coil sensor. And then we also installed multi-frequency GNSS antennas and 4 to 5 different GNSS INS devices.
Okay, thanks, Paul. So next question, I guess, is also for you. Let's try. Can the German and French colleagues provide estimates regarding the typical 1, 2, and 3 sigmas reported by your reference GNSS INS devices?
It's difficult to say as far as I remember from some test runs. So in good scenarios, for 1 sigma, in open sky areas, you can, without any correction service, for example, you can go a half a meter, for example.
Okay.
I can maybe complement the answer for the French side. So in France, so for the ground truth, we've used high-end INS with post-processing software with forward and backward processing and using RTK measurement, GNSS RTK measurement. So we the 3 sigma value reported by the reference by the INS after all these processes is about, well, it's centimeter accuracy, of course, in open sky with RTK, and in long tunnels like the one for the RER-B in Paris, so about 10 kilometers, something like that. The maximum standard deviation, 3 sigma standard deviation reported by the reference was about 1.5 meters of error. So as Bernhard mentioned, in long tunnels we lose accuracy, even with the reference, even with a high and INS. But yeah, this is a counterpart of using this kind of technology with respect to using track maps and odometer as was done in Switzerland. But this is still quite good accuracy for a long tunnel, and much better than what we can possibly obtain with our solution. So it's still useful to compare with.
Okay, so thanks. And I guess the next question is also for Paul. Paul, how did you know whether the error was due to the reference GNSS system, Germany and France, or the solutions, considering both setups had same sensor setups?
Yeah, this is a very good question. This was our struggle, that we, for example, don't have ETCS Balise reader in order to introduce an independent reference, so to speak. We were experimenting around for some time, for example, by using DB internal maps, to map matching to them, and try if this is a suitable ground truth. But we had even more problems because of jumpings, switches, and sometimes even parts of the tracks didn't exist. So the best solution which was possible in the scope of the project for us was using a high-grade INS system. Also considering that we had to build up the train during the time of the project in those 2.5 years. So this is as far as we came, so to speak.
Okay.
Maybe I can complement the answer of Paul. The idea of using a high-end INS with a high-end GNSS technology is to have errors far smaller than what we can have with our solution, so that the ground truth error is negligible with respect to the one that we have with our solution. So with respect to what I was mentioning before, if we have a centimeter accuracy in open sky or in let's say GNSS available areas, this is an error that is much smaller than what we can have with our solutions, TLOBU. So this is comparable, and even so there are some errors. This is negligible. So we are sure that the main errors that we see will come from the solution and not from the ground truth. But of course, this is not a ground truth that is CL4 level, so there is still possibility for errors at some points and in some places. But this is good enough for for the level of demonstration that we are making right now. But the ground truth quality will indeed be a topic for qualification in the future when we'll have a solution to qualify it.
Maybe I can also comment that we've discussed that inside the project team, and we've described various possibilities of. Can you still hear me?
Now again. Maybe you can repeat. I think Bernard is frozen.
Okay, I think we'll be back. Sorry about that.
Yeah, you're back.
Again. So yes, we've discussed various methods of how to demonstrate the accuracy of the different ground truths. They're also described in the respective deliverable, but we haven't had the time to actually perform that. And we are aware that in a future step more towards certification, of course, we will have to demonstrate the actual true performance of the ground truth to use it as a reference.
Okay, so thanks, Bernard, Valentin. Next one is, how is generated the ground truth trajectory? Which sensors? With map-aided fusion, independently from the sensors used in the final CLUG solution?
Again, that's different for the 3 ground truths. The Swiss ground truth currently only produces speed and position. We are also producing the speed vector for the front end of the train. That's all based on using the map and odometry data, but we are currently not producing attitude information. So pitch, roll, and yaw of the actual vehicle body. For that, we would have to use an IMU, which we have installed, but we haven't yet incorporated into the ground truth. The 2 other ground truths are producing pitch, roll, heading information and yaw information using their high-end IMUs.
Okay, so thanks to all of you for your questions and also for the answers. I think we now have to move on, and I will give it to Florian now.
Yes, thank you also for the Q&A, and I can assure there will be a last Q&A at the end of this webinar again, so we can come back to the questions, and you're also able to send in additional questions for the following topics. So the next topic is certification. Certification is another key step and important topic of the project, and let's have an overview and introduction to it. Please welcome Philippe Mros from NAVCERT. Philippe is the head of laboratory at NAVCERT, where NAVCERT is a certification body that was involved in this project. Welcome, Philippe.
Hi, Florian. Thanks for the nice introduction. Now I hope my screen sharing works. 1 second. Come on. Can you now see my screen?
Yes, perfect.
Perfect. So thank you very much. So also thank you very much for the introduction. As you already heard, the assurance of reliability and the safety is a key element to CLUG. There, our company NAVCERT is as an accredited laboratory and certification body, worked here in the assessment of GNSS measurement equipment, and sorry. And there, together with the cooperation in TUV South, we were involved here in the voluntary certification approach. So what we now it's moving. So what we have done within the CLUG project was split into 2 main tasks, let's say it like this. The first one was identification and validation of certification methods, and the second part, the prototypical certification, or better to say, prototypical certification methods. This is the general overview. What we have done here was, in the first step, we assessed methods and concepts for the validation according to to already existing standardization framework or already upcoming standardization framework. In the 5.8, we did then the development of the voluntary prototypical certification system for the train localization system. So to give a little bit of overview in which field we are moving, there generically you have to say we have two big differentiators in the certification environment. There we have the voluntary certification and the mandatory certification. The mandatory certification is the usually most complex one and is based on harmonized standards and on available regulations. There usually a notified body, which is also a certification body, can create such a certification if they got from a national accreditation authority or national accreditation body the accreditation that they can do it. And additionally, they are notified by a national authority, which is appointed usually by the national government to doing this, to get also that they are allowed to do it. We are here currently moving in the area of the voluntary certification because currently regulation, harmonized standards, etc. are missing for a GNSS-based certification. There usually 3 different types of voluntary certifications are available. One, the easiest one is where the certification body allows itself, so gives itself the qualification. This is, for example, for certain products which are available on the field. The case, an example can be put here as, for example, for Apple. The next level, let's say, of the voluntary certification is here we have already a qualification body, which is some kind of private association, a company, etc. So some kind of organization which defines some homogeneous rules up to a certain level for the nomination of a certification body. There, for example, the GSMA can be put as an example. The last field where we are moving here within the CLUG environment is that we have here the accreditation body as an authority from a national state, which gives the certification body an accreditation for a certain scope based on standards or on own developed certification scheme. Correct. So what we have done now then in CLUG was we defined a prototypical voluntary certification, which follows 4 different steps. Usually, the first step is that we set up the dedicated testing scheme, or better to say certification scheme, which reflects the already agreed on certification scope, which is also represented in the, for example, voluntary certification mark. The next level is that usually this test report is then reviewed on the laboratory level based on this 1725. And then the next level, then theoretically, if you want also to move on for the certification, so not only prototypical, is that this test report is then reviewed also by the certification body and accepted, and then usually also discussed with other additional partners. For this voluntary certification, we defined, for example, the requirements for the testing, the requirements for the certification. This then both was concluded into the definition of the conformance test procedures, or short CTP, for the different requirements, which then build the base for the project internal standard. Within the CTPs, different topics like input, output, test pace, fair criteria, test environment, etc. were defined. Within these conformant test procedures, also different test setups are applying, for example, simulation tests, record and replay tests, and field tests, like also Bernhard showed up to a certain level already. The last what I want to say to this slide here currently is that what we did for the voluntary certification and the certification mark, that we defined there voluntary certification for the position, velocity, and time of position, velocity, time systems for the usage in train localization systems, where we have 2 main objectives. The first one is the position, velocity, time, reliability, availability, performance, and continuity, and the second one, the safety topic. So what we have done then in the later runs of the testing scheme, we implemented for the validation of a scheme, a validation plan according to the ISO 17025, which consists then we go through all the CTPs, check on a according to the requirements, all the CTPs regarding the testing scheme, the testing method, etc., the identified KPIs, the identified inputs, outputs, the test and fail criteria, and also the reference information, if this fits together to the requirements which are stated in the 17025, which is here the basis for. Here we acknowledge also from a lot of other work packages, the already done work by the partners. There we have, for example, to highlight especially the work package 4. Within the CLUG project, we did here a high-level validation. Due to this, that we are still moving in a prototypical voluntary certification, so that not everything is already, let's say, put into stone, so that, for example, if certain topics are applying, we still have some freedom to adapt, for example. Correct. So what are the next steps for the certification, from the standardization point of view. So generically saying, we have two bigger goals, which is the assurance of the reliability, availability, performance, and continuity for the safety relevant position velocity system for on the train, so short the TLOBU, and also to transfer this prototypical voluntary certification method, which we have currently, to create a final voluntary certification scheme, or even to move further on. There we have then two major topics to tackle within a follow-up project, or however, which is the first topic is the finalization of the prototypical certification scheme, which, for example, is the finalization of the validation, especially of the PVT reference through calibration, qualification, etc. There we have to tackle that all the reference which is used as the ground truth, for example, fused corrected GNSS with odometry and IMU, that these are following the ISO 17025 requirements for reference system. This includes, for example, impact factor analysis, a measurement analysis, etc. There also a big topic which is a little bit challenging is the setup to connect to SE constants, so that we have a little bit the feedback also to some kind of calibration, which is for certain measurement equipment quite challenging. Additionally, which is a little bit included in the impacting factor analysis already, is to analyze the ground truth together also with the TLOBU regarding some critical scenarios, for example, so that we can exclude some certain common error topics. The last topic, and then including the finalization, is here the verification of the test scheme and the method. This would include, for example, a real-world testing campaign for such a thing. Additionally, the second topic would be the identification for the mandatory certification would be a development of a standards, which then could be, for example, forwarded to the European Commission to work on a regulation or a harmonized standard then.
Thank you, Philipp, for this great overview of a very complex yet interesting topic. All over the day now, we have covered many various aspects of the CLUG project so far. And I think now it's time to make a final assessment again and a conclusion of what we have seen here and what we have done in the project. So please welcome back Valentin Barrault from SNCF. Valentin is the CLUG project coordinator at SNCF, and Muthu Kumar from Deutsche Bahn. Muthu is the CLUG technical project manager at Deutsche Bahn. So the stage is yours.
Okay, thank you, Florian, and thank you everyone for being here together with us over the course of the entire day. It's been an absolute pleasure to answer all of your questions and to also understand the thoughts from your side as well regarding the work we've done. So thank you for that. And in this presentation, Valentin and I will try to summarize the results of the project, what we've achieved, and also highlight some of the key issues that we believe need to be addressed in future projects and how we can get there. So the first thing I would like to reiterate is that CLUG is an innovation and a research project, and it is our vision to bring the train localization system to a new era using digital maps and GNSS. As you've seen throughout the day, especially on the presentations from Work Package 2, we believe that such a new localization system can enable and foster new concepts such as intelligent traffic management and automation of the train operations, and also moving block. In addition, it can also help us to improve the operational quality of the service by providing a better localization performance, while reducing the capital expenditure and the operational expenditure of the railways when it comes to the localization part. Sebastian presented to you earlier this morning a detailed overview of the standardized interfaces that we believe are needed for modularization of the ETCS onboard unit, especially when it comes to the topic of the localization system and it being separated from the European vital computer.
CLUG was actually quite a large project in terms of its scope and in terms of the number of hours that was invested in the entire project. In the morning, you heard a lot about the mission definition and the system requirements from me and then later on from Sebastian. And you now heard about the prototypical certification from Philip. All of this was done in Work Package 2 and Work Package 5. Some of these deliverables are already public deliverables and they've been published. I'm going to give you a short summary of the achievements from Work Package 2 when it comes to these topics. And later in this presentation, Valentin will talk to you about a summary of achievements and the next steps with regard to Work Package 3, system design, and also the summary and results of Work Package 4. In terms of the requirements, I think the most important thing for all of us to take away from today's session and from the public documents that we've published is that the wider system of interest and the way and the methodology that we have used for specifying requirements in this project enables us to update the requirements, to update the system design as we evolve with our discussions with our European partners. We've defined clear rationales and detailed thought processes behind why we need these requirements and what it means. So every time there's an additional input coming from you or coming from the rest of the European initiatives, then we are able to then justify and update the thought processes from our side as well. And it's key to remember that CLUG is not a project in isolation. Majority of the system requirements that we have defined have already been transported back to the ETCS onboard unit modularization initiatives in OCORA. We've published the concept architectures as part of the ERTMS user group, and our colleagues in Shift2Rail, especially the demonstrators where Siemens, SNCF, and DB are involved, are using the operational scenarios that we defined in the CLUG project. Similarly, of course, the CLUG project has also benefited from all of these European initiatives as well. So these are the key achievements and the summaries when it comes to Work Package 2. In terms of what needs to be done next, there are a couple of key areas. One being start of mission, where we have not yet defined detailed requirements as to what happens when the system starts up in a cold start. This has to be addressed. And the second aspect is then track selectivity, where the system has to be able to provide us a track ID on its own without the use of any trackside infrastructure elements. These are the key areas which will be worked on in the future projects that we've identified. Dirk will show you the roadmap that we've identified for the future in the next presentation. But for the moment, I hand over to Valentin to provide you an update in terms of Work Package 3, Work Package 4, and what was done there.
All right, I think I took the hand on the presentation. Can you see my screen?
Yes. Yes, I can.
All right. Okay, so well, this is the CLUG concept that I presented at the beginning, and that was well, recalled several times in the presentation in between also. So nothing really new here. The idea was just to remind you last time the TLOBU and the, well, kind of wider system of interest of our solution in the train and outside the train. What we can say is that so we have still Euro balises on this scheme that we intend to use potentially in some places where we would need it, as you may have understood from the earlier presentation. So the idea is really to get rid of it as much as possible, but there might be still places where it's necessary to keep the required accuracy and safety level. So this is why it still appears on this picture. Regarding the track side, so well, the idea is to use Egnos correction, either coming from the signal space of the Egnos satellites, but potentially also from a trackside infrastructure and coming through the Euro radio channel. This would allow notably to have a continuous transmission of these corrections, something that we could not achieve with a signal in space, as we may be as the train will evolve in disturbed areas. Well, so I believe that's all important. That the only thing important to retain with respect to that. And if we now get interested in the TLOBU architecture that you also have seen several times today, maybe in a slightly different forms, as here the fusion and integrity filters are slightly more detailed with some kind of sub-modules, notably start of mission and strike selectivity. Modules that have not been defined and well, that have been defined but not designed in the frame of this project, and on which we will need to work in the future in terms of operational and requirement specification, but also in terms of design of the algorithm themselves. And also potentially exported constraints, notably for the start of mission. Regarding, so on this architecture, you can see the Egnos ground dissemination I was just discussing before, and for each sensor there is the FDE algorithms, fault detection and exclusion algorithm, that have been partly designed, but not fully, and they need to be robustified or fully defined depending on the sensors. So this is also another work, another task to be done in the future. This will help improve the accuracy of the system, but also the safety, as Pierrick mentioned during his presentation on the on the safety analysis. Regarding the fusion filter, which is here called localization, so we have implemented it. This is the main module that we have implemented during this project. We saw the fusion filter. This fusion filter uses corrections coming from Egnos version 2, the currently online version of Egnos. But we need to update it in the future so that it can take correction coming from the future Egnos DFMC service that is still planned only for aviation, but potentially, but we are also working with USPA to define an Egnos service defined for rail users based on the DFMC service, and maybe even more in some proposal we've made. So this will be something to do also in the future. This will help also improve safety and accuracy as for the FD. Regarding the integrity filter, which is the last big module that we have here, it was also mentioned that we have defined the equations and all, but only on paper so far. So we have this integrity concept ready. It has been tested, notably in simulations, as Pierrick presented, with some results that I will recall right after. But so we'll need to develop it and implement it in our demonstrator to be able to fully demonstrate this solution. And the last one that is important is to make this solution ready for real time, as it has not only been defined for post-processing so far. So now regarding the integrity and safety analysis that I mentioned right before. So regarding integrity analysis, Pierrick showed that we managed to have with a solution, the TLOBU solution using DFMC correction, we managed to have very good performance in open sky and well, good enough performance in suburban, but just at the limit, and performance insufficient in urban environments. So this is a good first good results that would need to be confirmed and better detailed. But we can at least from this result, the TLOBU solution that we have designed could be a good solution for a future product and would allow to remove some balises of the tracks, at least the one in open sky and probably part of the one in suburban areas as well. If we want to maintain good enough accuracy in suburban and urban environment, we'll need other complementary systems or sensors. For instance, we could use balises in these places to keep this accuracy at the required level. So this really shows that without balises it would be good in open sky, but in suburban and urban we may still need balises. That would be a solution. The other one would be to use a more performing Egnos service, more performing than Egnos DFMC, as this is the service that was used here for the simulations. So an Egnos specific Egnos for rail service with detailed with a specific service dedicated to rail could be used here. Regarding the safety analysis, so you've seen that we've reached with the current architecture a SIL 3 level, so not SIL 4, which is the targeted level. Several possible solutions are foreseen to reach SIL 4 or to reach at least the required necessary performance level. So it could be related to a refinement of the requirement, as it was mentioned by Arnaud at some point. We need to consolidate the safety requirements, the values related to these requirements, and another way would be to make some redundancy in our filter, to have potentially several filters in parallel to be seen, to be discussed. This is to be tackled in the future, and also to add independency principles. Also, we'll need to improve the FDE design, as I was already mentioning before. Regarding the hardware and software architecture, it will also need to be designed, as we already only focused on the functional architecture so far. So this is another point to tackle in the future to make a more complete safety analysis. Regarding now the accuracy, so we had both solutions. Both solutions were tested with respect to accuracy. We've seen so far some promising results, and it showed that actually several solutions could fit the TLOBLU, the CLUG requirements. We've seen some good performance in position and velocity for the solution A of Airbus, and some promising results with respect to the position for the solution of Naventic, with some improvements still necessary in position, but very good results on the velocity. So these two results are promising, and will need to be analyzed deeper and improved in the future with the help of all the data that we collected, and with the help of improvement like additional FDE in the filters. So regarding the topics for the future investigation, there is the work on requirements, where we will need to consolidate the preliminary performance requirement that we've made, and we'll need to tackle everything related to start of mission and track selectivity, as we already mentioned. And of course, we'll need to standardize the external interface of the localization module for the future TSI notably. Regarding technical challenge, well, I already mentioned most of them, but so there is a real-time implementation of the filter, the implementation of new modules like track selectivity, for instance, and the FDE. The functional architecture consolidation to reach notably SIL 4 with the hardware and software architecture design, and all this leading to a detailed safety analysis for a train-centric localization that will prove that we can manage that we reach SIL 4. So to finish, so I recall here all the public deliverables that we have published or are going to publish in the project. You can find them on the CLUG website in the page deliverable. The deliverables that have not yet been published will be very soon published in the coming weeks. We'll make you aware of that through our LinkedIn page. If you're following the CLUG project through our LinkedIn page, you will know exactly when it will be online. Bernard also mentioned that we'll make some public, some dataset public. This will also be made through the website with some information about it and links to download the public datasets. Right, so I guess that's all for these conclusions, and I will leave now the floor to Florian to announce what is following. Thank you.
Okay, thank you very much to both of you, Valentin and Mutu, for this great conclusion. And I think all of us today, we have learned a lot about the use of GNSS for the train localization and also the great work done by the entire team in the CLUG project. Congratulations to all of you, and nevertheless, a lot remains to do. And using the GNSS and the satellite navigation system all over Europe is a clear target by 2030 by the European Railways and USPA. But also, we need to work on the upcoming RTMS and ETCS standards and with regards to inputs for the future TSIs. So as a final presentation, let's now learn about more about the further general roadmap for the future of the digital rail system in Europe. And for this topic, I'm pleased to welcome Dirk Spiegel from Deutsche Bahn. Dirk is the technical lead for the development of fully automated driving from Deutsche Bahn. Welcome, Dirk. The stage is yours.
Hello, and thank you very much, Florian, for the introduction. So what do we have on the roadmap for the future? Can you see my screen?
Yes. Can you go in presentation mode? Perfect.
Yes. So what do we have in the future? In general, we are fostering at having the localization system ready by somehow 2030. The CLUG project was a very good first step to work on mission requirements and operational requirements, and to also demonstrate a first technical feasibility. But we have already seen from Mutu and also Valentin that we have quite a lot of stuff to do until we have a new localization system to enabling all the new system capabilities. So what have we planned in the near future to coming to a future localization system? We have basically 5 different parts. We have ambition number 1, which is detailing the business model and to basically show the positive impact of a localization system. We have the ambition number 2, which is focusing on ensuring interoperability on the European level and making sure that whatever we are doing here is standardized in the future as a precondition for a European-wide rollout. We have the ambition number 3, also focusing on next functions and operational scenarios, what we are concentrating on next. We have the ambition number 4, ensuring the quality and performance of the localization system, and also the ambition number 5, which is focusing on safety and security of this potential solution. So let me start with the ambition number 1. How are we tackling the investigation in terms of a cost-benefit analysis for the localization system? We are today already working in the ERTMS users group, the localization working group, on a cost-benefit analysis for the safe train localization. And I think it's already quite clear that we are tackling this topic in somehow like an onion. So we are starting at the core, where we are basically investigating CapEx and OpEx savings for the CCS topics. But then going further outside, we are also looking at additional benefits such as automatic train operation, TMS optimization, and then even further outside, we have topics such as passenger information, but the real-time information. So it's a quite complex task, but it is addressed, and we are going forward on this topic. Then we have the ambition number 2. How do we ensure interoperability? Interoperability is one of the Europe's main challenges. And I believe everyone who has some in-depth knowledge about railway knows that it's the thing to address. So the safe train localization system is a key for whatever is coming next. If it's level 3, driving in minimal distance, or whether it's fully automated driving, or also future CCS systems. So the localization system has to feed all of those system capabilities, and therefore is addressed on different topics or different initiatives. So on the one hand, we are aligning on the ERTMS users group for the localization working group to harmonize requirements and also mission operation requirements. We are further investigating and shaping the interfaces within the OCORA consortium for the safe train positioning system. The next steps we are working on is that we will concentrate some of our work in the technical enablers at the ERT European Rail Joint Undertaking, in especially the innovation pillar, where technical demonstrators are presented, but also working hand in hand with the system pillar, where the basis for future TSI changes shall be laid. This will for sure be a back and forth process. On the one hand, writing down specification, on the other hand, showing the technical feasibility until we have converged, hopefully by the end of 2026, by the end of phase 1. We further have the ambition number 3. So what are we focusing from the technical point of view quite soon? Digitalization opens a wide range of applications, ATO, ETCS, hybrid, and so on. What we have learned from CLUG, we have basically 3 core topics we have to address next, or we want to address next. On the one hand, it's the whole topic of track selective localization without balances. So is it possible actually to ensure a certain amount of safety without balances in the rails? The other topic we have is how do we handle the situation of start of mission, especially when we have a non-working code movement detector in the future. Furthermore, and that's one big topic, is how do we actually handle GNSS or the localization in GNSS denied environments? So we are going to tackle these topics by conducting a further innovation project and research project, such as CLUG. And also one idea or one proposal we have handed in is CLUG 2. And we are hopefully getting a positive response for the project soon. Ambition number 4, ensuring performance and quality. What we have seen today are the first, I believe, well, I found very promising results. So what can be done? When we are looking in detail on the results, we have seen that we have 3 core topics we want to address soon, such as transferring the algorithms from a backend solution into a real-time environment, also showing that we can handle real latencies, different signals, and also the messaging. That we also address the performance of new functionalities such as start of mission, and also how long it actually takes until the train is localized safely at the beginning of a train trip. And one very big core topic is to address a broader set of environmental conditions, such as heavy rain, which is a big problem today, snow, and other activities, other conditions. Also for this, we concentrate on future projects like CLUG 2, where we actually made a proposal for a real-time demonstration using an onboard computing unit in Switzerland as a playground for the real demo and to really test it under operational conditions. Europe's Rail is another good candidate, offering interesting opportunities for performance testing, especially the flagship area 2 in the innovation pillar is concentrating on developing those systems and then also bringing it together with the other enablers in the later stage of ERJU. Ambition number 5. What's left is the whole and very complex topic of safety and security. Safety, in my understanding, is by far the very important topic. And we really have to continue work on this topic. And I believe it's widely known that this is the basis also for standardization. In CLUG, we have already collected quite a large amount of data, which we can already use for safety demonstration and further investigate this topic. On the one other hand, we have the whole topic of security, which became after the start of the war in the Ukraine even more important. So in Germany, the railway system is classified as a critical infrastructure and therefore has to follow quite a lot of procedures. And looking into the next steps, we further have to investigate our system architecture so that it's also fulfilling the requirements of critical infrastructure. And this most likely will mean that we somehow have to have a redundant system for the case that GNSS is blocked or jammed or spoofed. Furthermore, we also have to look into new algorithms. Arno already mentioned it, I believe, today, about fault detection and exclusion algorithms that have not been part in CLUG, but most likely will be part in CLUG too. These are our core steps in the near future. Thank you very much, and I give back to Florian.
So I think you can give it to me, Dirk. So thank you, Dirk, for your presentation. And I see that the shared topics have raised some questions, and that's a good point for us to come to our last Q&A for the day. And so let's have a look at the question you have sent to us. And the first one is, I guess, a good question for Dirk to start. So any forecast when commercially usable products with SIL4 will be available?
In the timeline of the Europe's Rail joint undertaking, the series production or the TRL 8 to 9 for driving in minimal distance, but also fully automated driving shall be achieved by 2032. Since that requires a new localization fulfilling the new requirements we have based on the system capabilities, that is our core goal we are working on.
Okay, thanks, Dirk, for this answer. Next question is for Philip. Which is the validation strategy to demonstrate so low THR for ERTMS?
Yeah, that's a good question, because also in other areas, like for example, in the automotive with the SAE levels 3 and higher, they're currently discussing on this topic, and also some approaches are already in the field. And usually there's, with the combination of different test approaches, this can be achieved, but it is, yeah, still ongoing topic, let's say like this, where we are also in contact with certain colleagues on the TÜV sites, and also from the standardization regulation side there, we have some contact where we are exchanging on this topic.
Thanks, Philip. So next question, Mutu. Same question as this morning, as it was not really answered. Is it possible to prevent a rough state or anybody from jamming the GNSS?
If the question is about if we are able to stop anyone or a rogue state from jamming GNSS, the answer is no. At least to my knowledge and to the knowledge of many others, it's not currently possible to totally prevent jamming. USPA has already worked on preventing spoofing, and that there is an open authentication service that can prevent spoofing. And if the question is oriented towards how we are tackling this problem, then as Dirk mentioned, railways are considered as very relevant, and therefore there has to be fallback solutions when particular sensors are not available to work. So that's why we have a multi-sensor approach in the CLUG project, and we're not just relying on one sensor. I hope it answers the question. If not, please feel free to add another one.
Yeah, maybe I can add a few words. As for jamming as well as spoofing, we cannot prevent, of course, people from trying to do that, but there are some work under study for detecting and mitigating. So it's just like the police. There will be a need sometime maybe for GNSS police on ground, or surveillance also from space. There are also some projects for surveying jamming from space to detect jammers. But that's a general issue that is not specific to rail. It's for all GNSS users.
Okay, so thanks for your answers. And next question is for Bernhard. Is it reasonable to claim that the results of the CLUG project are promising and encouraging, considering that the performance of low and medium cost sensors have not yet been analyzed? If it is shown that high-end equipment are necessary in order to meet safety and performance requirements, then what is the estimated cost of the train localization onboard unit that CLUG has used?
Actually, the conclusion that we haven't demonstrated the use of low-cost sensors is not correct, because the data from the test runs from Geneva to Annemasse and from Ville to Le Verrières are from the Domino train, where we are using the low-cost sensors. So actually, we are demonstrating that even with using a MUBLOX receiver and a relatively low-cost MEMS-based IMU, we get very good results.
To complement what Bernard just said, the high-end sensors have been used to define the ground truth mainly. So not for they have not been used in the solution to provide the performance. They have only been used to define the ground truth with which is compared the result of the solutions.
We are very much aware that we have to use sensors which are in a cost range that is in the range where customers expect prices to be of products. So we are not aiming at using 100,000 euro IMUs.
Yes, and so basically for now, most of the analysis that we've made is based on the low-cost sensors. We've also recorded data with more high-end sensors, but we did not fully analyze it yet. The idea was more to focus on the low-cost sensors, as these are the ones that are the most interesting, because they are low-cost basically. So yeah.
So thanks a lot for clarifying that, and maybe you can continue, Valentin, because we have another question for you. On which part are applied the FDE techniques at the measurements level, for example, per sensors, at the sensors fusion level, for example, some majority voting or solution separation techniques?
Well, so it's applied at several levels. Arnaud will complete the answer if necessary. But so the idea is to apply some FDE on the outputs of the sensors to validate that the measurements are correct. I will just put back the slide at the same time. All right. And then to also apply it at the fusion algorithm level to validate that the output of the algorithms are okay. But so the one that we need to really define first are the ones here on this architecture. So right after the different sensors, to be sure that be sure to have correct values input to the fusion and integrity algorithms.
And then indeed, if you keep your display, we have in vertical multiple data fault detection and exclusion. That is the part at fusion levels.
Exactly. So 2 levels, sensors and fusion level.
And it's not a technical of majority voting or something like that, but the bank filter is a better approach.
Okay. Thanks, Valentin. So next one is, have you considered a GNSS independent solution in addition of the TLOBU, such as high-grade INS with digital maps fusion to reach a global SIL4 architecture?
I can answer this one. So this was not the focus of the CLUG project. Of course, there are other independent projects where such a solution is being investigated, but we believe in a multi-fusion approach where GNSS also plays a role.
Okay, thanks, Mutu. So I think the last question.
I could also I could also add that if we only concentrate on high-grade INS with digital map, the absolute part that I was explaining, absolute is not maybe the fully appropriate word, but for the absolute position, there is still missing something. So that means that balises should be kept on that solution.
Yeah, we need an absolute position at some point to be able to place it on the tracks on the map, and this absolute position. Even so, we use INS and IMUs and digital map to compute most of the position. You still need at some point an absolute position to first place the train on the tracks.
And it's the same for the speed domain.
And that
because else integrating the INS data only provide will provide a bias for the speed.
Another consideration is also the cost factor, because as you increase the cost of the IMU, then your solution is going to get more expensive, whereas you could potentially reach similar performance levels with a GNSS and an IMU tightly coupled solution as well.
And maybe just a comment from my side, we do have all the data available to do such testing, so we could actually discuss an algorithm where we only use very few balises for absolute positioning and then only rely on IMU and map matching and possibly odometer data. We do have the tools, we have the data, but we need to discuss the algorithm.
Okay, so thanks for the answers. And another question we are having is how much do the used low-cost sensors cost compared to the high-end ones?
I guess I can take this question. Well, when we talk about low-cost IMU here, we talk about IMUs in the price range of a few thousand euros to a few thousand euro maximum. And for the high-end IMU, we are talking about, for instance, that the one that we use for the ground truth, it's in the range of a few dozens of kilo euro. So that's for the IMU. For the GNSS part, the low-cost receivers of new blocks, it's a few hundred euros. And the high-end receivers that we can use for the GNSS, like Septentrio or Trimble, are more in the range of a few thousand euros. But the prices are also getting down, so yeah. let's say 1,000 euro.
We do have IMUs installed from about 50 cents upwards on the domino train, so that will be one of the steps we plan to do to analyze the differences. So we really want to explore the full spectrum of price range of sensors.
Okay. So thanks a lot for. Oh, sorry, Valentin. You wanted to add something?
Yeah, just to complement what Bernard said. So what we have analyzed so far, the data with the data, it's for the data that was analyzed with the domino mostly. It's with IMU in the range of a few kilo euros.
It's about 2 kilo euro is the IMU, and about 50 euro the GNSS receiver.
Okay, so last question for today is, does the test results and performance checked during rainy season and snow season? This is a good question for Bernard, I think.
Yes, we do have some data. We have the usual impacts on the different odometry sensors. So the tachos show more slip and slide. The radars show dropouts because they get covered by snow and ice. And that's going to be a discussion, what kind of odometry sensor shall be used and what kind of FDE algorithm.
Okay, so thanks, Bernard, and thank you for everyone who sent us the question and for answering. And I guess I pass it on to Florian again.
Yes, thank you, Jasmin, and thanks to all the people who provided those interesting questions and the colleagues with their great answers. So now it is time for the final part, closing remarks to this webinar and the project. And for this, I welcome and leave the floor again to Daniel Dupour from USPA. Daniel is the CLUG project officer at USPA, the European Union Agency for Space Application. Daniel, welcome back.
Thank you very much, Florian, and good afternoon once more again from my side. So first of all, I have to congratulate the whole consortium for the extremely good results of this project and the whole activity that, of course, took a little bit longer than expected, but it ended up with even wider range of successes. So what we have seen today is in the first place, very promising results, I would say, with which the community can be very happy on the basis of the tests carried out throughout CLUG project. This is different from the cases beforehand. So now we can say, if I may, that the environment should not be considered as a blocking point anymore. So technically, we have a solution that is possible or that potentially can overcome these barriers that are coming or stemming from the very complex railway environment. Then we also saw a very structured approach of the key rail stakeholders from across the railway segment having actually the same objective as USPA, which is to include and to aim for the inclusion of such a solution into the future TSIs and to have GNSS enabled ETCS hopefully soon. And we also have the institutional support at hand, again, from the European Parliament through European Railway Agency, which is well informed and on board of these activities. Also, the Europe's Rail Joint Undertaking is following. We are closely involved in ERJU as well. And from the space sector, meaning from our side and also from the European Space Agency, we are actually trying to do our best to prepare the necessary services in coordination with the railways as soon as possible. So for what concerns the next steps, it was already very well addressed by Dirk. Thank you, Dirk, for this. So to summarize, we need to prepare the service as soon as possible. to allow its release for testing, demonstration projects, and in the future, before the TSI is ready, also for full operational capability. Then we should continue to work on improving the technological readiness level of the CLUG TLOBU and work on the gaps that are still as identified by the consortium pending towards a couple of upcoming R&D initiatives. Of course, there will be a need either in frame of our projects or ERJU, maybe some tests and further demonstrations of the completed solution and the preparation of the inclusion into the TSI itself. So to conclude, simply in line with the last year's resolution of the Parliament on the state of play of ERTMS, I would like to turn to you again, to the EU railway industry and the railway undertakings to continue with the CLUG spirit somehow, to close these residual gaps so that we can hopefully see GNSS in the TSI soon. We will be closely behind. Again, I can say this for us and both for the support that we are receiving from the European Space Agency as well and the other stakeholders from the space segment. We will remain there for you to support you, and I hope that it is going to be possible in this wide and also fascinating segment of the railways to find a common conclusion of this topic and to ensure that we can also create this benefit coming from space and turn it into a reality finally. So thank you very much, everybody. Thank you for your attention.
Thank you very much, Daniel, for these motivating closing remarks. And now, finally, I leave it to Dirk Spiegel again one last time to provide a big thank you and the formal event closure to the entire team of the project and the participants of the webinar today. Please welcome Dirk Spiegel from Deutsche Bahn. He is the technical lead for the development of fully automated driving. Dirk, you are live.
So, hello everyone again. When we come to an end of a project, I always feel a little bit sad, to be honest, especially projects where such a great working harmony is, as in this one, and also where we have received quite a lot of very good results. So I can remember the day actually when we sat down quite soon, quite close to this room I'm right now sitting in, and we decided with FBB and SNCF to basically conduct this project. And I'm very, very happy to see what has come out of it. And also the roughly 130 listeners in the top, more than 60 questions we have discussed and agreed on today. Makes me really happy that we also worked on a very interesting, very fundamental and very important topic. So I would like to thank especially OISPA and Daniel Lepur for funding this project, and I hope we also find a way in the future to continue on all the open questions we have still done. And I also want to thank the whole CLUG team. Everyone has done a great job. I believe it's very, very good what we have achieved in the roughly 3 years. And I want to thank especially Mutu and Valentin for leading this project most of the time, and also all those other contributors who are not so much in the spotlight, those two. So also thank you very much, Jasmine and Florian, for the facilitation today and the Jasmine, Florian, thank you very much. I wish you all a wonderful afternoon, and I'm very happy that you all came to this event today and that you showed your interest. Thank you. Have a great evening.
Yes, thank you also from my side to everyone, and also to Yasmin and Mutu for organizing, hosting this event, and moderating. Yeah, and a big thanks to all the presenters today for being available and sharing your knowledge and your results with us today. I think it was a pleasure to have you here today, and we learned really a lot. Yeah. Some final words about the content we have shared. So the final deliverables are currently in progress or done and will be soon available on the website and published. Some public deliverables are already available, and we have posted the link to the website in the questions if you want to have a deeper look into it and learn more about the actual results. The whole webinar has been recorded and will be made public soon. And we will let you know as soon as it is available, so you can share or rewatch or have a look at the slides again. Thank you everyone for your kind attention, your questions, and also the entire team, especially here, contributing to the project, working so hard for so many months, being so dedicated, and in the end, so successful. Amazing work, and thank you a lot.